Okay, welcome everybody. Please take a seat. Can you hear me? Welcome everybody. Please take a seat. So, welcome to this year's edition of Eurostrings. And to start off this event, I welcome Mikael Fogelström, Director of Nordita.
Thank you very much. And again, welcome to Stockholm and I can. Okay, very good. So once again, welcome to Stockholm and Albano area, and also Nordita, which is located here. I think you're lucky you have a late summer week ahead of you, and quite a few people have made their way here to join this conference. As I was introduced, I'm the current director of Nordita, and I think the field and this topic is quite close to the core of Nordita. I don't know how much you know about Nordita, but it has been around since '57, initially in Copenhagen, and now lately here in Stockholm. And it is the Nordic Institute for Theoretical Physics, and the whole mission of the institute is actually to promote excellence in theoretical physics, but also to promote young scientists on their path and career ahead. So for a long time, one of the core missions was actually to bring young scientists into academia. And we usually have this bragging number that we have produced on average 2 professors in the Nordic university system per year. So there has been some success. But I'm not here to brag about that. I'm here to welcome you. And this is a conference that has been going on for quite some time. I understand 30 years or so. So that's quite good, quite persistent. And I guess, although many are young, as far as I can see, not all of you are first-time offenders, but you probably come here year after year and meet and network with old colleagues, and also new. And that's perhaps the core idea of these kind of events. I had a brief glance at the program, and it looks very nice and well composed, that you have these overview of the field, you have keynotes, and then topical presentations, as well as posters. And you also have a lot of space for actually interaction, networking, and establishing new networks, maintaining old, and probably pushing the field forward, I understand, because as every grant that we have, or any big financing of research, we always need to find new ways of maintaining them, and that's an important. So with that, I actually will just give the word over to, who's next? Okay.
Thank you very much, Mikael. Okay, so let me welcome you on behalf of the organizing committee of Eurostrings. So my name is Magdalena Larfors, for those of you who don't know me. And we're very happy to welcome you to this beautiful city of Stockholm, which you can see here as it looked in the olden days. It has grown a bit since, and we are very happy that you have made it here. So this meeting is made possible by the generous support of Nordita, together with Uppsala University, the Cost Network Theory Challenges, Vetenskapsrådet, so the Swedish Research Council, and Wilhelmsfonden. Some practical information before we start. So because we have funding from Cost, you need to sign. We need signatures from the participants every day. So please, when you come here, there will be lists where you can put your signature, and please do that so we can actually pay for what we do here. There will be coffee and lunch breaks outside of the room, and this will be pretty evident when it starts, how it works. If you want information, so all information about the meeting, the schedule with the talk titles and abstract, and the information about the poster session can be found online. There you can also find our code of conduct, which I will say a bit more about, and you will find more information about some special events that happen throughout this week. So of course our main focus are the scientific talks and the scientific presentations that we will have. But there are also some special events. There's an outreach event about science in turbulent times, and a panel discussion on Wednesday about funding opportunities for our field. And I strongly encourage you to participate in these events. So our code of conduct you can find in detail online. And if you have any questions about this, you're very welcome to talk to us organizers. So the important pieces of information are here highlighted. So the European String community is committed to creating an inclusive and non-discriminatory environment, difficult word to say. And we just ask all of you to act in accordance with this, so please behave professionally. This is not strange for any of us. It's just a reminder of how we interact in our field. This is a very nice poster for our very clear outreach event that we will have. Now it's a bit heavy, so it takes a bit to load. This will happen tomorrow. We have an outreach event called The Role of Science in Times of Geopolitical Uncertainties. This will include a public lecture by Robert Dycraft, who's very well known to our field and who is now ISC President-elect, and Ronald de Bruyn, who is Director of Cost at the European Union. It will also include a panel discussion with Robert, Ronald, and Mikael about this topic. You're all very welcome. We have already sent information about this, and there's a link to register for this event because we have this capacity that is in the room, but there is still space, so if you do want to participate, please register. Okay, and that was all for me, and now I will hand over to Alessandro.
Okay. Can you go back a slide? One more. Perfect. Thank you. Well, first, a last piece of business from Magdalena. The fire exits are located over there and over here. So take note of that in case of emergency. Other than that, hi, my name is Alessandro Sfondrini. I am the chair of the Cost Action Fundamental Challenges in Theoretical Physics, and it is my pleasure to welcome you on behalf of the Action to this meeting, which is not only an iteration of the Eurostrings conference series, but is also the general meeting of our Action. The Action, for people that are members, they probably know, half of you, roughly speaking, are member of the Action already, but it's structured along 3 lines: a working group in gauge theory, one in gravity and holography, and one in low-dimensional systems. And it's about trying to find non-perturbative answers in any of these fields and gain new insight in physics, using, of course, also interactions with mathematics. If you are not a member of the Action, you are very welcome to join. That's the best way to be aware of our future activities. I will announce something later on towards the end of this meeting. And for all information on how to join, you can just use this website, theorychallenges.eu. I would also like to inform you about who are the people that help us run this Action. So, as well as myself, there is Piotr Sulkowski, who helps with the general running of the Action. And then there are people that help with particular aspects, such as grants that we award for travel grants, activities that are related to particular topics, so to each of the working groups, the organization of schools, and general communication strategy. And you see, I've marked in blue the colleagues that are actually here during this meeting. So feel free to approach them if you have questions specific to the action. If you're curious about some of these aspects, you can just go and talk to me or any of these colleagues. And finally, I should mention Elvira Pedone. She is the manager of the action. She's in charge of all the administrative aspects, and she has a desk just by the entrance. Is where you sign. If you are a member of the action in attendance, there is the signature sheet, as Magdalena has pointed out. But for those of you who are reimbursed by us, please go and see Elvira, because she will help you set up your claim. It's much easier if you do it while you're here, and then it will be very easy to submit it, so you don't have to email back and forth, and you will get your money right away. It's important because if somebody is late, it sort of holds up everybody else, and then it becomes a bit unpleasant. Okay, that is all that I wanted to say. I will have something more to say about the cost network system and how you can take part or even apply for a new cost action in this panel discussion about European funding that Maddalena has already mentioned. So stay tuned for that. I hope that you will take part in that panel. I think it will be very interesting. But for now, this is all that I wanted to tell you. So thank you very much for your time.
Is there a pointer? Right.
Okay. Oh, does that work? Can you hear me? Yes. Okay, so let's start the scientific part of Eurostrings, and we start with a review talk by Sakura Schäfer-Nameki, and she's.
And
Okay,
it goes, oh, amazing.
So she's going to talk about generalized symmetries.
It works, yes, yeah. Sorry, I wasn't paying attention. Okay, sorry, he was telling me something. Okay, thank you very much to the organizers, to my chair, for introducing me and for inviting me to give this overview talk to this absolutely stunning place. I mean, it's really a fantastic campus here. It's very nice to see sort of everyone come to this location. You might note that there's a slight change in the title, but now you're in this room and it seems the doors are locked, so you can't leave. And I changed the categorical because it's, you know, it used to be generalized if you didn't read the title, because I think it's important that we get used to this terminology because it's going to stay with us. And one of the things that I would like to convey in this talk is it's nothing mysterious, it's nothing strange, and something you should learn just like the way you've learned group theory. So what is a global symmetry in 2025? Well, if you ask the generic person in this field, they will give the answer. It's a fusion higher category. But this is literally just a statement. Take your favorite quantum field theory or quantum system and look at all the topological operators of any dimension. They can compose in a particular way. And that's the thing that will form this kind of gadget. Here I'm talking about finite symmetry. Is this working, by the way? Okay. Finite symmetries, so not continuous ones. They should be included into this, but for finite symmetries, this is the answer. So a quick recap, if you've sort of not paid attention in the last 10 years on this subject. Of course, in 2014, the first generalization was from standard global symmetries acting on point operators to higher form symmetries acting on extended operators like Wilson lines, Toft lines, and so on. But then in the last 2 years, there are these so-called non-invertible or categorical symmetries, which compose beyond the sort of group-like composition. In particular, they don't have inverses. So that's why they're called non-invertible, and it's really synonymous to this categorical language. They compose, you take a p-dimensional object, you compose it with another one, and out comes a sum with some coefficients. They could be integers, but they could also be actual partition functions of series. So this is the generic structure that we see in topological defects when they compose in the generic quantum field theory. There are many reviews and there are many high energy focused sort of overview talks. There was one at Strings this year. There was one in 2023 by Shuhang, and I gave it one last year at Strings, giving also some view on how these are realized in string theory. I realize this is Eurostrings. Now I'm going to declare I will not talk a lot about string theory. Andre will not like this, because I think one of the most exciting things that actually happens in this field is that there's been an enormous, really stunning kind of synergy between all kinds of fields that until, maybe a few years ago were relatively disconnected. High energy, condensed matter, math, quantum info, and AMO. And if you don't know what AMO is, it's atomic, molecular, and optics. And literally, through these symmetry structures, these things have sort of come together. And they're questions that you ask in one field, you answer it, and then you can use that to answer other questions in these neighboring fields. And I want to explain to you how this works, and in a particular instance. Let me just sort of, of course, each one of these blobs have their own agenda, but let me sort of just quickly talk you through what these people are after, and we know what we're after. We want to understand global symmetries and their implications. In math, they're interested in the theory of such things and the classification, and I think the most exciting sort of new result is that there's basically classification of all symmetries, discrete symmetries, in 2+1 dimensional systems. So that's sort of a math output that is extremely useful for us, and you can use it to study 2+1D QFTs. I won't go into details. You'll have the slides later. You can look at this. In condensed matter, of course, people are interested in phases of matter, phase transitions, lattice systems, so that you actually can do numerics on them, simulate them. And in fact, there's been a lot of interesting work independently on these categorical symmetries in such lattice systems, developing sort of numerical methods, but also trying to understand what are actually anomalies of such things. And of course, as a high energy physicist, we're also interested in anomalies for such symmetries. Then there's this field of QI and AMO, and there are loads of questions that, to us are a bit more alien. So they want to construct a fault-tolerant, error-correcting universal quantum code and can be implemented in some future, near future, hopefully, quantum device. So there are all kinds of things that we might not connect directly, but at the end, I hope to convince you that some of the theoretical things that we do actually play a role there as well. Okay, so you might still think secretly, sitting there, well, this is still exotic, physically probably useless, niche subject for theorists somewhere in high energy. And I think basically after this talk, I hope you will get some idea that that's not the case. So the first thing I want to do is give you sort of a reminder, what are the constructions? And they work in any dimension. You pick your favorite dimension, and I can give you a construction of non-invertible symmetries in quantum systems that you could study. So this is sort of like a universality kind of thing. They're like these kind of structures. But then actually there's the second part where I really want to sort of show that there's a concept, a theoretical concept that's very familiar to high energy physicists that can then be used in all these interactions. And the first thing is to actually classify phases. And there are pure state phases and mixed state phases, so also noisy systems can be studied. And then study of anomalies. So anomalies like Toft anomalies, they constrain RG flows for such categorical symmetries. And finally, there's some direct connection to these quantum simulators and actually constructing some new interesting codes. Okay, so let's recap what we know about non-invertible symmetries in high energy physics. So this is sort of setting the tone, like where these things actually occur. And the sort of classic example is coming from, if you have a system that has a self-duality, this is sort of a vehicle to construct a non-invertible symmetry for you. So the canonical example is the Kramers-Vannier duality in, for example, the Ising spin chain or model, a transverse field Ising model. And at the critical point is Ising CFT has a symmetry. When I square it, it squares to 1 plus another symmetry generator that's a Z2 symmetry. So that's a canonical sort of non-invertible symmetry composition. So how do you see this in the spin model? Basically, you send G to 1 over G and this ZZX kind of transverse field easing model, and it maps basically these two terms into each other. That's not a symmetry for generic G, but at G goes to 1, it becomes a symmetry, and that's precisely N. Now you can play this game also in any other even dimension. In particular, this is sort of what kicked off this whole field. Namely, in 4 dimensions, space-time dimensions, we can look at a self-duality symmetry of quantum field theory. And when we do that, we can sort of look at if the QFT is equivalent to the QFT after the duality, we can construct completely analogously to this a non-invertible symmetry for the QFT. Right, so this is the canonical example is, for example, if you like supersymmetric field theories, you can look at SO3, theta equals to pi, and that'll have that kind of symmetry defects. But it also works in any even dimension. So you could also say, well, it also works for the 6D theories. And indeed, in 6D 2,0 theories, you can construct, now using self-dualities of 6D theories, which are Green-Schwarz automorphisms. So they map the BPS string charge lattice into itself. You need to compose it with some additional topological things like gauging the 2-form symmetry. Right? So here this was a 0-form symmetry. This is a 1-form symmetry. And this is now a 2-form symmetry. So it's always the one that when you gauge it, it goes back to the same degree of form. So in this case, it's a 2-form symmetry, it goes back to itself. You can construct non-invertible duality defects. So one example is the SO8 6D theory that can be made into good quantum field theory. And this has sort of an S3 worth of non-invertible defects, which you compose from these Green-Schwarz automorphisms, which are in these black arrows, and then also some topological manipulations. And any loop that you form here will give rise to a non-invertible defect. So when you compose that with itself, it'll give a non-invertible fusion. So in fact, right, this tells you in any even dimension, you have a self-duality, you could construct these kind of non-invertible symmetries. Another example is if you have an auto-automorphism, like charge conjugation, then you can gauge that, and you also get a non-invertible symmetry. So the simplest example is in any dimension, the O2 gauge theory. You start with U1, and you gauge the charge conjugation. Basically, if you look at, say, the U1, so it has these kind of topological defects. I'm agnostic about the dimension here, but basically what charge conjugation does is it changes the alpha to d minus alpha. So the invariant combination is a sum. And now, even naively, if you calculate the square of that, it'll be the sum of other terms. It's a little bit more subtle than that, but that's morally speaking what's happening. So whenever you have, for example, charge conjugation, you gauge it, you get a non-invertible symmetry. And then finally, the one that you probably all have heard in phenomenological applications also is whenever you have an ABG anomaly, be that, in some QED, or it could also be with an anomalous R symmetry or something, then you get a non-invertible symmetry. So here you have basically a non-conservation equation. That's the ABG anomaly. So the right-hand side spoils the conservation of this current. You can sort of reinterpret it as saying there's now a symmetry where I sort of shove this back to the left-hand side. I declare the symmetry generated as not just exponentials of this star J, but I stack it with some additional TQFT. And when I do that, then this here is now closed because it satisfies exactly this equation, but it comes at the price that this now is non-invertible. So if I compose it n with n dagger, it gives something that's not the identity, but what's called a condensation defect. So whenever you have an ABG anomaly, you can also equally talk about a non-invertible symmetry. Okay, so these are basically 3 examples of how these things occur in your favorite QFTs. Now, one criticism is all of these things are kind of obtained by gauging, so how come they have some physical implications? So I want to convince you that there are some interesting physical implications that you wouldn't have known had you not studied these symmetries. So the first one is this so-called modified crossing relation that goes back to this paper here by Copetti, Cordova, and Komatsu. And it's really sort of a hallmark of if you have a non-invertible symmetry, you can't just do your standard rules of scattering and say in some integrable systems, but you actually need to modify that. So the idea is if you have a 2D CFT, a rational CFT, it has these non-invertible so-called Verlinde lines. These form one of these categorical structures. And if you now have a relevant deformation that preserves some of these to an integrable theory, so massive theory, then in fact the scattering gets modified by the consistency with that symmetry. So what they found is that basically if you have this sort of standard scattering of kinks in these theories, then the word identity with these symmetry generators imposes that now there's not a standard crossing relation, but gets modified basically by this fraction, this quotient of dimensions of these topological defects, which doesn't have to be 1. So this is a sort of really changing how you solve crossing. There's also a similar thing in this paper by Minwala and others in 2+1D, where they scatter anyons, so one-dimensional topological defects. So this is clearly a very exciting area to explore further and see what kind of implications we get. The other implication is, so if you have a non-invertible symmetry, you can ask, it's a slightly more condensatory question, but it also is something you can ask about phases of quantum field theories. Namely, when you have non-invertible symmetries, do they need to new IR phases and phase transitions? And so canonically, we would say, well, if you have a group symmetry, then Landau taught us, well, any second order phase transition is basically given by some symmetry breaking for group G. I'm taking G to be a finite group here. So the gapped phases are where G is spontaneously broken to a subgroup. Right, so this is literally one-to-one from the Landau story, so some subgroup H. And any phase transition is a Landau phase transition if there are two subgroups HI, and they classify they correspond to these gap phases, and then there's a transition if one is a subgroup of the other, and then the order parameters are basically sort of trivial under one and non-trivial under the other. That drives this transition. The question is, when you have a categorical symmetry, how do you now extend this to, what are the rules here, where this also is sort of specialized back to this group-like case. And so for this, basically, now many of these words will not be clear yet. We will get to this, but I want to just illustrate, this is a pretty sharp, simple sort of summary of how Landau transitions work. If you have a category S, some non-invertible symmetry S, in particular, this is very clear for 1+1D, then the gap phases are in one-to-one with what's called gap boundary conditions of the symmetry TFT, or so-called Lagrangian algebras of the Drinfeld center of S. So this is generalizing, there's a subgroup of a group, and that's sort of the unbroken subgroup. And then the phase transitions are basically, you have two of these algebras. If they intersect and there's a consistent algebra, then there can be a phase transition between these two things. And that generalizes this statement that one group is a subgroup of the other. And the order parameters also come from particular types of topological defects in the system. So it's extremely clear, parallel to the system that we have for groups, but now for categories. Okay, so this is just to say, first of all, in d-dimensional quantum field theory, you can construct these non-invertible symmetries, and we've seen some, very sharp predictions of these two things that we didn't know, and so they seem extremely worthwhile studying. But the story is even better because there's all this synergy with other fields. And so I put down these blobs in the following because it sort of is something that comes from this high energy thinking. It's actually very closely related to holography. A lot of you are working on holography, so maybe that perspective is very helpful for this. But it goes into quantum condensed matter and quantum info, and then also anomalies, of course, are relevant for all these fields. And then finally, there are these applications to these codes. And all of these three things, they all are sort of tied together with one thing that I would like to explain, and that's sort of the thing that I would like you to take away from this talk, namely what is the symmetry TFT, and sort of this, there's sort of some synergy through this principle of the symmetry TFT, essentially having different incarnations in different fields and being extremely useful. So we'll talk about what that is. So the symmetry TFT is also called often the symmetry sandwich because of the structure of two slices of bread and some filling. And then in this paper by G and Ren, they also called it topological holography. It's closely related to holography, but it's really, for a high-energy physicist, I think the wrong terminology. Because what is it? It's basically you have your theory T with some symmetry S. So S is a finite symmetry, but it can be non-invertible in d dimensions. And the symmetry TFT is just gauging that symmetry in d+1 dimensions. So if you have a group symmetry, the sim TFT is just a finite group gauge theory, a Dykov-Witten theory in d+1 dimensions. But more generally, it's some more complicated topological field theory. If it's for 1+1 dimensional systems, so the boundary is a 1+1 dimensional theory. Here, let's start here with this theory, this 1+1 dimensional theory. Then, in fact, the bulk will be 2+1 dimensional. It's what's usually referred to as topological order in 3 dimensions. And the topological defects of this are called anyons. So they're like lines, but they don't have necessarily spins that are either bosonic or fermionic. It can be any value, any fractional value. So that will be one of the setups we'll be discussing in some more detail. But what's sort of the paradigm here? This is this picture. So the sim-TFT is basically this theory with the symmetry action S is equivalent to this 1-dimension higher TQFT on a slab with 2 boundary conditions. One boundary is realizing the symmetry. So all the symmetry defects live on there. So if you take all the topological defects and you push them to this boundary, they generate the symmetry S. And on the other side, you have all the dynamics. So here you put your n=4 super Young-Mills, or your favorite quantum systems and lattice model. And on this side, you actually put the symmetry defects. And in the bulk, you have this full TQFT propagating. And what is sort of the utility of this? It sort of separates the symmetry aspects from the dynamics. So everything you want to know about the symmetry can be studied essentially from this, usually ignoring this boundary. So there'll also be these things, these defects that stretch between the 2 boundaries, and those become charged operators in the actual theory when you collapse this back down, right? There's a TQFT, so the size of this interval is completely immaterial. You can collapse it, and you get this d-dimensional theory. And the statement is these 2 things are equivalent. So these charges are basically topological defects stretching between both, and the charge is calculated by looking at how topological defects braid in this TQFT, how they link with each other. Okay, so that's the sort of bare bones summary of the sim-TFT. To actually do these 3 steps, these 3 applications, we need to extend this a little bit and look at sort of this sort of double sandwich or this club sandwich. So we have now 3 slices of bread and fillings. And now the question is, so here I have the sim-TFT for symmetry S, and now an interface to another sim-TFT for another symmetry S prime. And I always want to think of this as basically a larger symmetry, and here there's some reduced symmetry S prime. So these kind of interfaces can come from what's called the condensation of defects. So essentially, I will define certain ends of topological defects. They will end and some will propagate through. And so this is sort of after condensation, the reduced topological field theory. So if you study this system, and you really just need to understand, say, 1+1D, what's going on with this, then we can apply it to these 3 things. And it's always the same math applied to 3 different physical systems. And it's sort of a pretty cool application of this thing. So it's sort of a buy 1, get 3 for free. What is this sort of club sandwich? Well, really, it's about this interface, right? So the interface is telling us how these 2 topological field theories are connected. And let's stick to 1+1D. So then these are topological lines. The bulk is a 3-dimensional TQFT, here and here. And now these lines can do various things. They can either end, they can go through, or they can just bend down. They can't end, they can't go through, so they just confine. So these are the 3 scenarios. One is the anion ends. That actually defines the interface. So the interface is sort of given in terms of the lines that can end on it. So that's the condensation of anions. This is usually given in terms of a sum of particular integer linear combinations of such topological lines or anions, and they have to be mutually local. You can't have them end and not be mutually local. So this locality is basically what means condensable algebra. Then there are the ones, if you take them in and then they can't end, but they can't go through because in fact they braid non-trivially with these red ones. So these yellow ones, basically they're not mutually local with the ones that end. So they kind of just stick around and they bend down and they confine on this interface. And then finally, they're the ones that can't end, but they sort of go through. They're the deconfined ones, and they define what is this reduced TQFT. If S prime is trivial, this is nothing other than a gap boundary condition. It's just an interface to the trivial theory. So the case of the standard SimTFT is sort of packaged into this as well. And in that case, this algebra isn't just sort of mutually local, but it's also maximal, and these are called Lagrangian algebras. So studying Lagrangian algebras is basically studying these interfaces to the trivial TQFT. Okay? So this is the picture that you should keep in mind when I'm talking about these interfaces. And now we can look at examples. And the first example is for groups. So if you have a finite group, you can ask what is sort of the TQFT that lives here? What are these type of interfaces? So for finite group, the SimTFT defects are labeled by conjugacy classes and irreps of the centralizers of elements in this conjugacy class. And that's important in particular if the group is non-abelian. If it's abelian, I'll give you a much simpler description of this, but essentially this is sort of the structure of these defects. So each one of these lines here is now labeled by that kind of data. And the question is now, what are these mutually local things? So they all braid around each other, and there's a complicated structure. And basically, one can classify these condensable algebras, these interfaces, also if the group is anomalous. And they're basically given in terms of subgroups, normal subgroups of the subgroup, and some additional cocycles. And this is basically where also this whole thing will connect back to this original Landau story. One example is, of course, if I take all the irreps, so the identity conjugacy class, meaning the whole group, and the irreps of the group, if I take this to be the algebra, then this is just an interface to the trivial theory. It's a maximal thing, and it's on this interface we realize the group G. Right, so we have lines that are in the irreps ending. The things that talk to this, the braid non-trivially, are the group elements. So in fact, on that boundary, we generate the group G. Vice versa, if we take the conjugacy classes with the trivial irreps, then we generate the dual symmetry, which is rep G. So the irreps of the finite group G, they also form a non-invertible symmetry. So this is basically non-invertible for non-abelian groups G. Okay, so I can see some eyes glazing over, so let's actually think about this for Zn. There's no funny non-invertibility, but it might sort of explain a little bit what these things are. So if I have a Zn, zero form symmetry in 1 plus 1D, so for example, Z2 in some, two-dimensional QFT of your liking, then the SimTFT is basically just a Dicke-Witten theory for Zn. So it has background fields B1 and the dual field A1 and B1. And there are topological defects, which are just the holonomies of B1 and A1. But because of this BF term, they will braid non-trivially. Right? So each one, E to the n and M to the n is 0, but it is 1, excuse me. But when I exchange them, because of this BF term, they will pick up a phase, and it's given in terms of the linking of these gamma 1 and gamma 2. Right, so these are some loops, and now if they sort of link, they will give a phase, and basically this is how we measure that this is sort of a system of now lines that are not mutually local. And these gap boundary conditions that are sort of giving the group symmetry and the dual symmetry are just now take all the E's, all the powers of E's and all the powers of M's, and they generate the Zn or the dual Zn symmetry. In this case, the representations of Zn are, again, isomorphic to Zn, so there's not much interesting stuff happening. But now you should imagine, for the non-abelian case, that's not true. In fact, in this case, you get this non-invertible symmetry from that boundary. Okay, so that's sort of just to put this into context. And then now, of course, other algebras, which now give interfaces that are, for example, sums of e's to a certain power only. So for Z4, it could be 1 plus e squared, for example. And they're classified by the subgroups of the group that you started with. Okay, so that's sort of, how this fits in. And now let's apply this to the phases. So first question is, can we classify pure state phases? And the answer is yes. Basically, the sim-TFT sandwich, we start with a symmetry, we put the symmetry and the symmetry boundary, and then any other sort of physical boundary that's sort of describing the dynamics, which now is a TQFT, so it's again a gapped boundary condition, will give rise to a gapped phase with that symmetry. So classifying the gapped phases is one-to-one with classifying these gap boundary conditions of the sim-TFT. So, and you can get all kinds of things. You get spontaneous symmetry breaking phases, and then these local operators that come from these stretched line operators, they give rise to the charged operators, and they give also the transformation under the remaining symmetry, the broken symmetry generators. The special instances when you have only the trivial operator stretching, that can be a trivial phase, or what's called a symmetry protected phase. So there can be sort of not local operators that are order parameters, but string-like order parameters. And those you would get by ending a line here and then stretching it down. So it can't end here, but it can sort of do this kind of L-shaped configuration, and you get a line operator that's attached to a point as an order parameter. Then this is just to tell you, this is literally, you can put this into work. So the simplest case is when you have a representation now of the simplest non-abelian group, S3. There's a two-dimensional irrep with this non-invertible fusion. 1 minus is the sign irrep, and E is the two-dimensional irrep. So this is a, sort of a very straightforward, decompose the irreps of S3 into the tensor product of irreps back into irreps. And there are, from this analysis, 4 gap boundary conditions, and these are the associated phases. So you get the number of vacua read off from the number of lines that can end, and then the symmetry action from the braiding with the other topological defects. Okay, and then there's also a story about the phase transitions, and that's now where we use this club sandwich with an interface. And here the idea is very simple, that if I have a sim-TFT for symmetry S, like some categorical symmetry, and an interface to another smaller symmetry S prime, I can construct out of phase transitions for S prime, phase transitions for S. So that's essentially this kind of this map between these TQFTs allows us to do that. So that's sort of how we then model the phase transitions. I actually don't want to discuss this more because I've talked about this on several occasions. I really want to get to these new applications, which are a little bit less in the high energy sort of comfort zone, because they really answer things that we may not be immediately interested in, but it sort of uses exactly the same technology. So mixed state phases is sort of another question, right? So you have, usually in your lab, you don't have sort of a nice pure state, but it's noisy, there could be at finite temperatures, so there could be all kinds of things that disturb the system, and you still would like to kind of describe what kind of phases you could have. And for this, one needs to understand mixed state phases and sort of what kind of constraints can symmetry still give in such a context. So here we don't have a sort of just a Hilbert space with some pure states, but now we need to talk about density matrices. So we have some Hilbert space H, but now some operator psi like this, and it satisfies rho squared is rho, then it's just a pure state, but normally it won't satisfy this condition. And it's Hermitian, so this is going to be an important condition. The question is, if you have a system that's only described in terms of such a mixed state, it can also happen by the way in holography. There are many systems where you have this, of course. What can symmetry still tell you about that? So symmetries in mixed states aren't sort of as sort of sharply defined as in the pure state case. We just act on the state and you want it to be in some representation. there are two notions. One is called the strong symmetry. So here it says you act for group symmetry with a unitary on you take the product with the density matrix, and it's just a phase times the density matrix. And then there's a weak symmetry where you need to conjugate. And of course, a strong symmetry is also weak, but a weak symmetry need not be strong. So now these two slightly, refined notions of symmetry, and that sort of works for invertible group-like symmetries, which are realized in terms of unitaries. For non-invertible symmetries, you have sort of some fusion, and here I'll assume it's something like S as dagger is 1 plus some sum of other defects here. So you have basically the structure, it goes to identity plus some other stuff. Then you actually can write this in terms of the strong and weak symmetry thing is basically a statement about you act on the left with this, or you conjugate and you get phases in both. Here a phase and here the mod of that phase. Okay, so that's sort of the kind of structure which now would like to study the phases of. So one trick how to deal with density matrices is to actually purify this, so actually map it to a pure state. And that, of course, comes with some constraints. You can't just map a mixed state to a pure state. Here, basically, you flip this cat into bra into a cat, and you get psi bar now in a double Hilbert space. And this kind of state, you could now ask, what is the notion of strong and weak symmetry? So the strong symmetry now says you have now two Hilbert spaces, a left and a right. Strong means you can act on the left, and it needs to be essentially invariant, or on the right, it needs to be invariant. And the weak symmetry says you have to act with both at the same time, and then it needs to go back to itself. So this is sort of now a way of entering now this pure state classification into this mixed state business by purifying to this double Hilbert space. And of course, once you are at that point, you can then also extend this to in this purified state also is called the choice state. So you can now look at the SIMTFT classification of these kind of mixed states. By looking at now the doubled symmetries, you have a left and a right symmetry, and there's this sort of funny thing that in fact you hear complex conjugated. Now there's some symmetry where if you switch them and you bar, so the swap star, it needs to be a symmetry of this density matrix, purified density matrix, so these symmetries actually need to satisfy this relation. So now the question is, if I have this pure state classification for phases, can I now also get the mixed state classification? So which boundary conditions of the SIMTFT for this doubled symmetry give rise to strong symmetries, to weak symmetries? What kind of properties are there? And also, is any phase of the SIMTFT also a mixed state phase? So there were actually two groups in the condensed matter, quantum info, working on this for group symmetries, and we did this for categorical symmetries, and we put this out in the same day, and we all looked at the same, it's all basically the same idea that you double it, and now you can actually describe these mixed states, but it comes at a particular cost, because not every symmetry Lagrangian, so gap boundary condition, is in fact giving rise to a density matrix once you go back to the reduced Hilbert space. So only certain Lagrangians, they have to be invariant under this swap star symmetry, and they need to give rise to positive definite density matrix. So there are conditions on this that then actually give you a more refined or a smaller set of phases that are consistent for these kind of systems. So these mixed phases basically now come from looking at Lagrangians that don't factorize into left and right. And the interesting types of phases are that you can break a strong symmetry to a weak symmetry, but you can also break now a strong symmetry to a weak symmetry partially and have sort of a trivial phase. There are all kinds of now mixed strong, weak SSBs and SPT kind of phases that sort of enrich this symmetry classification. So just to give you an idea of how this works for Z2. So these are basically, back in terms of the sort of density matrix formulation, a strong symmetry basically that's unbroken satisfies this kind of relation, and we can translate that into the SIMTFT. For Z2 strong symmetry, this is a simple sort of, exercise of these left and the right anions, now M and L, as I introduced earlier. And then there's one that doesn't factorize, and that gives sort of this phase is basically, you have this strong Z2 symmetry, and the weak gapped phase has only this anion that's sort of diagonal. So this means the E anions basically don't exist on their own as E left and E right, but actually only in this combination. And so that indicates a strong to weak SSB phase. Okay, so from just the SIMTFT, we can read off what is the property of the phase that we get in this after collapsing this back to a two-dimensional system. Okay, so for groups, this is not that interesting because you could study it also in other ways, but now we can we can apply it to this RAP-S3 again, for example, or any other non-invertible symmetry, and you get now these phases that are mixed, strong, weak, symmetry breaking phases for RAP-S3 that sort of model somewhat the pure phases, but actually have a slightly more refined breaking pattern because you could go from a strong symmetry to a weak symmetry and so on. Okay, so that's basically so there's also, okay, so I should talk about this very briefly because I promised that this sort of sandwich picture will resurface in each of these topics. Essentially, if you want to start with a symmetry that's weak, so it acts at the same time on the density matrix from left and right, then you could model it in terms of starting with a strong symmetry and sort of condensing to a diagonal symmetry. So very similar to how I did this thing with this here. This is basically going to a weak symmetry now because you get this diagonal anion stretching here. So essentially, you can model a weak symmetry by taking the SIMTFT for the double, for the strong symmetry, and then condensing sort of a diagonal and going to the weak symmetry generators. So essentially halving sort of your SIMTFT. The interesting thing here is that not every symmetry that you put in here can actually be made weak. So this is easy to see that if you have generic fusion rules of this type, and you have this weak symmetry condition, and then you want to make these compatible, then you run into a problem just sort of, plugging this in twice. You get this here, but it also needs to be that, and the fusion, he'll give all these terms. And so now you need to have relations that, in fact, you tell you what is WC with rho, WD dagger. So in fact, you can't make any non-invertible symmetry weak. And in fact, so one nice class of symmetries where you can make at least part of the symmetry weak are these sort of like the Ising symmetry category. So here, basically, there's a non-invertible defect n that fuses n squared to 1 plus the Z2 generator. And we can make n weak and keep the Z2 strong. So what this basically means is that on this side here, all of these become just some factor times rho, and on this side here, you still have this non-invertible generator. And so this gives you from what's called, so Ising is just what's called the Tambayamagami Z2 category. You might have heard of this. If not, then there's now, for any abelian group, there's essentially a duality symmetry, like I explained at the beginning. And if you use that, you can get for any abelian group a Tambayamagami symmetry. And in fact, when you do this construction of making the duality weak and keeping the Z2 strong, you get a Ty Z2 Z2 as this reduced order on the right-hand side here. Okay, so that's sort of applying these things to phases of various making, pure state phases, mixed state phases. You might ask, do you actually really get interesting new phases? Like, 1 plus 1 dimensional phase is a little bit boring. That's just a, number of vacua and maybe some relative Euler terms. So in 2 plus 1D, you can apply this and get some genuinely new phases in the sense of there could be a vacuum structure for a non-invertible symmetry where you have two sort of universes. They're exchanged, so they're partial SSB phase, but then each of these have a different topological field theory in it. So you have two vacua, SSB phase, but each vacuum has a different TQFT. So that's a very exotic kind of phase that hadn't been seen before, and it's interesting to study what these could be used for. Okay, so let me head to the third application, and this is something that I think may be closer to everyone's interest because it's about sort of RG flows. And again, I will tell a story, and then in the end, we'll use the sandwich to solve the problem. So this is a very useful investment to learn about these sandwiches. So we all like Toft anomalies because they constrain RG flows. If I have a theory in the UV and I want to go to the IR, what do? I look at things that I can track through the RG flow, and Toft anomalies are one particularly strong kind of tool at our disposal. Now, usually, we have for group-like symmetries, we can measure, we can really quantify what is this anomaly. There's some cohomology class or something. But when it gets to categorical symmetry, it's more coarse. So it's more like, is the symmetry anomalous or not? It's a yes-no question. And in mathematical terms, this means is there what's called a fiber functor. It just means, can you trivialize the symmetry? Is it non-anomalous? Can you make it trivial in DIR? So one thing that obstructs sort of this being a very simple exercise, Toft anomaly matching, is that there's sort of three things that can happen, in particular in higher dimensions. The symmetry might just trivialize in the IR, or there can be new symmetries that emerge in the IR, or there can be really more strange things like what's called fractionalization or transmutation. So symmetries of a particular degree don't stick to their degree. So a zero-form symmetry can transmute to one-form symmetry or something. So these are kind of things that mix up the game and make it more complicated. And for non-invertible symmetries, it's even more stringent because there it's not even clear what's a symmetry, what's an anomaly. There's, as I said, this criterion, the fiber functor, which just says if you have a category and you have a map to the trivial symmetry, and that satisfies some criteria, then that's actually telling us it's non-anomalous. But it doesn't tell you if it's anomalous, what is the anomaly, right? So that's what we would like to quantify, what are these Toft anomalies. So what we did with my two postdocs, Andrea and Christian, and my student Johan, is to actually formulate this kind of anomaly matching, to actually quantify what that is. In particular, in 1+1D, this can be made completely precise, and we have lots of examples in higher dimensions. And again, the symmetry TFT plays an important role. Now, these pictures, they look like symmetry TFTs, but they're not. Okay, so now you better pay attention for a second, because this is not a symmetry TFT picture. This is just a quantum field theory. This is a QFT, and this is the space-time, and there's no sandwich here. So a global symmetry basically is made out of topological defects, so they should be robust under the RG flow. And indeed, Guyot already noted that if you have a theory in the UV, and here there's some topological defect, and you do on one half space a relevant deformation, and then you flow to the IR, right? You get this half space sort of interface and an RG interface. And that interface models sort of the RG flow. So for groups, we can now track what happens to these topological defects very easily. Namely, I have a map from the UV symmetry to the IR symmetry, and basically they have to satisfy some H3 cohomology class, for example, with G, U1 valued, and the pullback of the IR symmetry needs to be the UV symmetry anomaly. So for categories, what we're proposing is, what replaces this is there needs to be between these two categories a particular type of map which has to satisfy consistency with the composition of defects and various other consistency conditions, and mathematically it's called a tensor functor. So what basically RG interfaces should correspond to are tensor functors. So when you have a UV theory and an IR theory, and you go with your topological defect through this RG interface, D maps to this F of D. Okay. Now, that's sort of telling us how symmetries would map, or how two sets of symmetries could be consistent with UV and IR. It doesn't tell us yet what is actually the measure of that anomaly. And for this, we need to look at a short exact sequence of such functors. So C is our symmetry category. And now, like with groups, you can embed a category and you can project. And basically, if this is sort of such that the image of I is the kernel of P, it's a short exact sequence. And if it's exact, it implies that N and I can map n all the way to trivial. So n is anomaly free, right? Because n can map to a trivial category, so I can trivialize it. So in fact, if I have a C and I have such a sequence, I can trivialize n. So n is always the bit that's, in the RG, if I can wash it out. Whereas S can potentially be the non-anomalous part. And so in fact, if you pick n to be maximal, so there's no other n that can sit there that's contained in a larger n that can sit in such a sequence, then we basically have sort of the maximal core of the anomaly on the right-hand side. And we call these things, these anomalous simple categories or ASCIIs. And so they're basically the measures of the anomaly of that categorical symmetry. So you write down C and you need to find N and S, and that's quite complicated and super annoying, and you don't want to do any of these mathematical manipulations, but you can recast it in the SimTFT, and then it becomes a very simple kind of exercise in these algebras and condensations. So this is our RG interface. So this is our space-time. Now I basically pop out the SimTFT. There's a symmetry boundary now in the front, the physical boundary in the back, and this is filled. And this is the purple bit is what became of the RG interface. And I can project it also down, and then I get this picture of here's the SimTFT for the UV, for the IR. This is when I collapse it, the interface, and now there's a symmetry UV and a symmetry IR. And I want to understand what kind of things are now okay between what kind of symmetry boundaries can I put here that are then giving rise to a tensor functor. So a tensor functor basically gives, again, one of these interfaces in the SimTFT. And the rule is very simple. This thing here gives rise to a tensor functor if and only if I slam it onto it's topological, so I slam it down to the UV boundary, it's equivalent to the IR boundary. That's the condition. And we can prove this quite generally. And now we can also do all these other things. We can do injective maps. It means that there is basically on this side here that all the ones that end on the interface, they basically also end on the symmetry boundary here. And the surjective maps basically means that these are so-called magnetic algebras, so there's only the trivial anion that can end here. And so then a short exact sequence becomes a SimTFT, now a triple sandwich. And we have the N symmetry boundary, the C symmetry boundary, the S symmetry boundary, and these guys are satisfying these conditions up here. And finally, the condition for this sort of minimal ASCII kind of thing is basically saying that if you have such a sequence, and now your category is such that it doesn't have any of these surjective maps into it, so basically there's no non-trivial magnetic algebra, then it's an ASCII. So that's a criterion that you can now check extremely efficiently. And since my chair is telling me that I have very little time left, I will very quickly tell you how it works for groups. Then I'll give a non-invertible example, and I'll leave the quantum info applications for the discussion session. So for group symmetries, we would like to reconstruct in this way this pullback of the anomaly class. So let's say we have a normal subgroup and the projection. Then in terms of categories, this means this. And now the question is, can we now, for example, see two different types of anomalous sort of cores of that symmetry? So if we take, for example, Z8 with anomaly class 4, so this is the class 4 and the H3 of Z8 with U1 coefficients, then there are actually two sequences that both basically have the anomaly free part is a Z2, and then the projection is a Z4 with anomaly 1 or anomaly -1. And if you package this back into the SimTFT, it just means you get these kind of pictures. And indeed, there are two types of interfaces here that go to Z4 with +-1 anomaly. So this is just recasting stuff that we know for groups. But now we can also look at non-invertible symmetries. Right? So there I don't know what is an anomaly. But what I know is that I should be able to sort of trivialize everything except for these ASCIIs. So the ASCIIs are these sort of core bits of anomalous symmetry. So the first example would be Ising, but Ising is itself an ASCII. So that's sort of actually a minimum building block that you could use to build anomalies for some categorical symmetries. So the next one is the Tambayagami Z4. So here you have n squares to all the generators of Z4, right? For Z2, it was the generators of Z2. And there are two types of such SIMTFT configurations. Both of them, again, trivialize Z2. In the middle, we have the Tambayagami Z4. And when you look at what type of interfaces you have to project onto, so these are these now ASCII components. There's a Z4 with omega 1 and a Z2 with a mixed anomaly. So it means you can, in this non-invertible symmetry, trivialize the Z2 along the RG flow, but you will always either have a Z4 with anomaly 1 or a mixed anomalous Z2 left over. And that you can't trivialize, and you need to match it in the IR. And of course, once you have this machine in place, you can apply it now to high dimensions, the applications that generalize the Wang Van Witten stuff, and then also fractionalization, also space-time symmetries. So this is basically the world is your oyster at that point. And because we have, you might wonder, why do you do it with the symmetry TFT? Well, first of all, I don't even know how to formulate this in high dimensions because we don't have enough structure in terms of what are these kind of interfaces, these tensor functors in high dimensions, and what are these properties of projective and injective functors. But we do know these interfaces, right? Crucially, the SIMTFT is something we can also construct for, say, four-dimensional quantum field theories. So there's lots to explore. In particular, I think for continuous symmetries, where we also have the SIMTFT, it would be very nice to actually understand how to construct such anomalous core contributions to the symmetry categories. Okay, 2 minutes. Okay, 2 minutes. So 2 minutes applications to, this is literally just to whet your appetite and tell you, okay, you can even talk to people that do lab physics. There are two applications. The first is we have all these phases, these new phases and phase transitions. Can one realize these in some actual, quantum simulators? And indeed, for example, this REP D4 symmetry, which is sort of like REP S3, but it has advantages that you can realize it on qubits. One can really write down a protocol how to put them into some cold atom lab and so realize them in terms of these Rydberg blockades. But a more theoretical, interesting thing is some of these higher form symmetries and also the categorical symmetries can be used in the context of improving our understanding of quantum codes. So one sort of direction is using higher form symmetries like Dijker-Witten theories for higher form symmetries, high group symmetries. It's mostly done by Po-Cheng Sin and Ryohei Kobayashi and others. But then the other application is to what's called magic state preparation. And that's where our friend, the SIMTFT, comes back. So there were two papers earlier this year which essentially use, again, this kind of condensation interface to construct what's called magic states. So magic is a technical term here. In this case, it just gives you a way to then do universal quantum computation. And what these people have done is, I will just show you the picture. Take the SIMTFT for D4, embed the Z4 one with an interface. We now know how to do that. Condense it back down to Z2. If you pass a state that's what's called Clifford through this, you get a magic state for some non-Clifford gate. So, and that can be explored in many, many directions. And again, it uses literally the same kind of mathematics of these SIMTFTs. Okay, so I hope it's clear that these symmetries are a very rich structure. There are lots of applications. I think the future, one of these things, one of the limitations maybe, or sort of the focus has been on finite symmetries. What about continuous symmetries, space-time symmetries, and sort of really explore the full scope of these anomalies? Because once we understand the anomalies, it'll give us new handles on QFT or G flows as well. Okay, thank you for your attention. I know what the question is. What does it have to do with string theory?
I'm going to ask an easier question. I'm kind of curious about your point of space-time symmetries you work to.
Ah, yes, of course, yes.
Can you reveal something about
Yes, this is a thing that will appear, well, hopefully in a few days. So this is with Nicola Dondi, who's somewhere here in the audience also, and Fabio, Iñaki, and Hotat. So the idea is the SimTFT is essentially you gauge the symmetry into bulk. Well, we've seen that before. It's like holography-ish. Yeah, that's why condensed matter physicists call it topological holography. But it's not quite. So even if you look at space-time symmetries, continuous ones, what you get is not necessary, right? All I want to model is the global symmetries. So then you can ask, what is it when you gauge into the bulk, this space-time, say, Poincare or conformal symmetries? And what you get is something that in low dimensions is just going to be like gravity, 1 + 1D gravity. It's going to be exactly a BF theory for these symmetries. And that's the SimTFT. But in higher dimensions becomes more distinct from it. But there's a clear connection. So essentially, what this allows us to do is study symmetry breaking of conformal symmetry to Poincare, these kind of things. In fact, stuff that Fiona, who's sitting right next to you, has studied in the past as well. So it connects that kind of direction to the symmetry TFT. And I think there are many applications following from that, but at the moment it's just about sort of writing down what is it SimTFT and what are the boundary conditions. Yeah. So. No questions. Okay. Boris.
Can you just comment on the challenges in extending to continuous symmetries?
Well, the first question is, how are you gauging? Are you gauging a flat or with actual dynamical gauge fields, right? But here we're just writing down BF theories for continuous symmetries. And that's been done also in these papers here, again by Nicola, and also I think Nikhil is in the audience, who've written down for internal symmetries, the SimTFTs for, say, a U1 or a non-abelian group. So it's a bit more messy because there's no structure like a category that we know, but then also it's mostly not non-invertible. So it's a little bit, it has different challenges.
There's no full classification. There's no full classification.
Of what? Oh, boundary conditions.
Symmetry breaking patterns of these generalized.
Yes, so I think, sure, but here these are not necessarily generalized, right? They're just U1s, SUNs. So it's interesting to ask what you can actually concoct. So there was a recent paper in 2 dimensions by Jung-Cheng and others where they had non-invertible space-time symmetries in 1 + 1D. So one could consider such things. There are also finite non-invertible symmetries, of course. So in condensed matter, you could have translations that are non-invertible. But they're slightly different. So you're asking about continuous. So in continuous context, these are usually just vanilla group symmetries. Okay, thank you.
Okay, well, thanks very much. First of all, thanks very much to the organizers. Thanks for giving me the chance to speak. So I guess for a strength conference, this is a slightly unusual talk in that I'm actually going to try and tell you about how string theory might be related to the standard model, to the real world. And particularly, I'll be focusing on Yukawa couplings from string theory and the kind of progress that we have made on this, I believe. So this is work in those papers, but there's a lot of prior work together with those people here. Okay, so the plan is, well, I want to tell you about Yukawa couplings in case you don't remember, and I want to tell you why they're typically hard to compute in string theory. And then I want to tell you about how we have managed to overcome this difficulty and talk a little bit about a tool which has to do with machine learning. And so this part is a little bit separate and is maybe useful for you as a tool for other applications as well. So that's why I'll spend a little time on that. Then I'll give you an example where we actually carried this out explicitly to get some examples. The examples, they're not realistic at this point. So that's what I talk about in the results section. And then I will tell you about attempts of making this realistic and actually get the Yukawa couplings as they're observed. Okay, so you may be aware, or you may be not aware, that it's now possible to engineer string models relatively straightforwardly, which have exactly the spectrum of the standard model, or I should say, the spectrum of the MSSM. This is sort of cleanly possible in those Calabi-Yau compactifications of the heterotic E8 times E8 string, and so this is a clean spectrum in the sense that the only extra fields that you have are not charged under the standard model group, so they're moduli. And so given this situation, from a physics point of view, there may be three questions that you can ask. So within those models which have the right spectrum, can you get physical Yukawa couplings as a function of moduli, of course, in the first place? They will always be functions of moduli. And can you calculate these? If you can do this, well, can you get to something that's actually realistic, that will reproduce, in the end, the masses of the particles that we observe? And then finally, if you can do that by picking some point in moduli space, well, then finally you have to address the question of, can you actually stabilize the moduli at that particular point, right? So these are three pretty hard questions, and in this talk, I will only address the first two of those. Okay, so let me remind you about Yukawa couplings. So these are at least up to a certain energy scale, n=1 supersymmetric theories. So this comes first of all as a superpotential with couplings Y here that are the holomorphic Yukawa couplings, and that you can often compute analytically in many models. But of course, string theory come with a non-trivial Kähler potentials. So the matter fields C here, they have non-trivial Kähler metric in front. And as the standard model Yukawa couplings are defined relative to canonically normalized fields, you will actually need to compute both of these objects, the Y and the K, in order to make a comparison with what we observe. Unfortunately, these matter field Kähler metrics are much harder to compute. They're not holomorphic. And this is where the difficulty lies, as I will tell you in a minute. So you need to compute both. And well, here's just an example for the up-Yukawa coupling, which we'll discuss later. So this is the up-Yukawa coupling. You need the Kähler normalization of the left-handed quarks, the U quarks, and of course the up-Higgs. All right, so what are the models that we can achieve those nice particle contents in? So there are heterotic E8 models on Calabi-Yaus with some bundles. So you have a Calabi-Yau threefold, a freely acting symmetry on there. You have an observable vector bundle V over this manifold, which is consistent with the symmetry and with supersymmetry. And you typically pick those structure groups which are SU5 or some subgroups thereof. And you have some hidden sector that you also need to specify in certain ways. There's extra hidden sectors, possibly from 5 branes. They all hang together with some anomaly condition. And eventually, as you initially get gut groups from these kinds of bundle structure groups, you go to a quotient and you introduce a Wilson line and you break your gut group to the standard model group. That's roughly how it works. And there are lots of choices here. And for most of these choices, you will not get anything. Of course, that's anything anywhere near a realistic model. But if you do make the right choices, and that's where the difficulty has been for many, many years, and that's now clearer how to achieve. If you do make those right choices, then you do get the MSSM and nothing else, plus moduli, and of course, whatever you pick up from those hidden sectors here. Okay, and so within those models, there are various classes. There is sort of the traditional class, which is the standard model class. So I should perhaps go back here and say, this is about how exactly you solve this anomaly conditions. You can solve it by switching the hidden bundle off, by switching the C off, and by setting V equals to T of X. That's one solution. That's often called the standard embedding. So that was the traditional way of doing it. But of course, that's very limited because your bundle is basically locked to the tangent bundle. So there's only that one possibility. So this is how string phenomenology started many, many years ago. And there was a recent paper there calculating Yukawa couplings within this setting, which is a very nice test, because within this setting, you can actually also calculate them analytically and compare. So then there's a class which is much wider, but it's still relatively simple because it uses just line bundles. So it has, as a structure group of the bundle, an abelian group, which is basically a bunch of U1s. And they will appear as additional Green-Schwarz type symmetries at low energy. And in this case, we know something like 10 to the 5 examples where we can get the exact MSSM spectrum. So it's a very large class. And then finally, the most general class would be models with non-abelian bundle groups, such as SU5. And that's a bit more difficult to handle. They're not as simple to handle as these line bundles. So there's a certain lower number of standard model cases known there. So I will, in this talk, focus on these line bundles because they are the simplest case with some, I mean, these are not completely distinct. They sort of tend to sit in the same moduli space. So you can often deform starting from line bundles to non-abelian bundles. I will also discuss a little bit those non-abelian cases later, but I'll start with those line bundles. Oops. Okay, sorry. All right, so why is it difficult to calculate those Yukawa couplings? So how does it even work? So you have a certain number of matter fields, Ci, and geometrically they are related to bundle-valued one forms on your internal manifold, which are these new i's here. And they are harmonic, so they're effectively representing first cohomologies of various kinds of bundles, which are related to the original bundle V. And the holomorphic Yukawa couplings, which was one of the ingredients that's needed, is this kind of integral here, which, as you can easily see, is invariant under change of the representative. So if you change this by something exact here and transform the integral, you integrate by parts, everything is sort of del bar closed here, then that is invariant, which means for this kind of integral, you do not need the harmonic representative. In other words, you do not need the metric on the space, and that's why it's effectively topological. And that's why you often are able to calculate this analytically. Now, this is very different here. This has a star and a bar, and so there's a metric in here, and there's a bundle metric in here. So if you do the same change of representative here, this will not be invariant. So here you really do need the harmonic representative to do the calculation, which means you need the Ritchie-Flat metric on your Calabi-Yau manifold, you need the Hermitian-Yang-Mills bundle connection, and in the end you need these harmonic forms, harmonic relative to those metrics, and all those things are basically not known. And that is the main difficulty, and that's why it has been not calculated for many, many years. So the upshot here is that in order to do this, you have to essentially solve complicated differential equations on your Calabi-Yau manifold. And so I want to tell you next about a general method for solving complicated nonlinear differential equations using machine learning, which is the tool that we've been using to do this in the end. So this is sort of a little diversion away from the main subject. And maybe I just, for those who haven't come across it, I just want to give you one slide on neural networks. So what are neural networks? So think of neural networks as function families, f theta, with a certain in and out dimensions and a number of parameters theta. So they parameterize the function family, but they're not just any function family typically. They're typically function families which are constructed by function composition from simpler building blocks, which are these little f's here. And what are the, well, here's just a bit of terminology that's used in this case. So the depth is the number of compositions that you carry out here. The width is the dimension of the vector spaces, and these various little f's here are called the layers of the neural network. And one example for what you might choose for these little f's, which are referred to as fully connected neural networks, is just some affine transformation of your vector with a matrix W and some bias B. And then there is a slight nonlinearity here, which might, for example, be this nonlinearity, which is called the activation function, which is meant to act component-wise on the vectorial argument. So that's kind of the most simple neural network. And the idea is, of course, that somehow you want to adjust these parameters theta in order to approximate some function that's either given to you by data or explicitly in some way. Okay, so what do we want to do with that? We want to try and use that to solve differential equations. So here is just some sort of schematic differential equation. And the idea will be that we'll use the neural network to represent the prospective solution to that neural network. And so how is this going to work? So we select some what is called a training set, which here means we just select some set of points on the domain on which this differential equation is defined. And then we define a loss function, which essentially measures the extent to which the differential equation is satisfied on those points. So we just evaluate the left-hand side here on this training set, these points xi, and then square it up. And there are possible other terms here which might represent boundary conditions that you might want to impose on your solution, etc., etc. Then with that loss function, we perform what is called a gradient descent. So we change the parameters along the negative gradient to find a minimum of the loss function. This is just gradient minimization of the loss function. And the hope is that once you've done this and you have found a minimum theta naught of your loss function, then that neural network with those choice of parameters will be a good approximation to your solution to the differential equation. Right? So that's the idea. Okay, so how are we going to apply this to our problem, which is to calculate all those quantities, the Ritchie-Flat metric, the bundle metric, and the harmonic forms on the Calabi-Yau manifold? So we have those various differential equations. The one for the Ritchie-Flat metric is called the Monge-Ampere equation, which is this equation here. So that's an equation essentially for J, the Kähler form, the omega, think of the omega is known. And we write our J as some reference J that we know, plus del bar phi. There is a mathematical statement here that phi is in fact a globally defined function on the Calabi-Yau. And our loss will then be the extent to which for a given phi we fail to satisfy this Monge-Ampere equation, which is sort of the equation that guarantees Ritchie flatness. It's the same as Ritchie flatness. And what we represent by the neural network here is this function phi. So that makes it a bit easier than representing a metric, because you only need to represent a scalar function. And then we do something very similar for the metric on the bundle. So there is a very similar equation, sort of analogous to the Monge-Ampere equation. We write that as some function beta times a reference metric that we know. We define some loss, which quantifies how much we fail to satisfy this equation. And the neural network is represented, or represents this function beta here. And then finally, for the harmonic L-valued forms, the bundle-valued forms, we do similar thing. Sorry? Oh, that's the, when you insert that in here, you pick up a source here on the right-hand side, which is coming from beta. That's rho of beta, yeah. And same here. So you write the harmonic form as a reference form plus something exact that's supposed to be chosen, so it makes it harmonic. And when you put that in here, you pick up a source, which is that rho beta, and so this measures then the deviation from how much this equation fails to be satisfied. And as before, the rho, the sigma, sorry, is the quantity that the neural network represents. And as I said, all these reference quantities are things that we know, so we can basically write them down analytically. As sort of think of Fubini's Studi metric. Yeah, so there's something like that. Okay, so the example model is one on a very simple manifold. So this is a manifold defined in the product of 4 P1s as a tetraquadric. So zero locus of a polynomial that's quadratic in each set of variables with some Z2 times Z2 symmetry and some sum of 5 line bundles as the vector bundle, and that is the spectrum. Yeah, so this is exactly the standard model spectrum. The only thing that's interesting here is, or that's sort of on top of the standard model structure, is that these various particles are charged under the U1 symmetries that go with those line bundles, and that's what these, that's essentially what the cohomology number here, or the line bundle number indicates. So if they are sitting in the but if they're coming from the second line bundle, it means they're charged under the second symmetry. If they come from the fifth line bundle, they're charged under the fifth symmetry, and so on. So there's a way in which the topological origin of these particles correlates with their charges that they pick up at low energy. So we have a standard model with sort of 4 extra U1 symmetries that constrain the structure. And in fact, these U1 symmetries, they constrain the structure of Yukawa couplings in this way, and also of the Kähler matrices. So if you focus on this for a second, you can see that this model is not likely by itself to give you something realistic, because this is only rank 2, right? We clearly need 3 non-zero masses, and also the mixing angles are supposed to be small, so the 0 here in the top entries is not great either, right? So this is not going to be a realistic model, but that wasn't the point of this exercise to begin with. If you pick some random model, the chances that it will be realistic are basically 0. The point here was to show that you can actually do the calculation. So we want to calculate the physical masses for these, for this example, of which in the up sector there will only be 2 in general, as we'll see in a minute. These 2 happen to be degenerate also, so there will in fact only be 1. So how does the calculation work? Schematically speaking, well, we start by computing numerically the Ricci-Flat metric on our Calabi-Yau. Right? Then once we have that, we can then calculate all the bundle metrics on the relevant bundles to do with the matter fields in L2 and L5, and with the Higgs on L2 star times L5 star. And then once we have those, we can then go on to compute the harmonic forms that correspond to all the particles that are involved in those Yukawa couplings. So all in all, you have to train 11 neural networks to find all these quantities. And then once we have all these, so every single one of these quantities is basically then a neural network on your computer. You can then use Monte Carlo integration to evaluate those integrals. So here are some details about how this is done technically. So there's a certain number of training points. There's some sort of specification of your neural network. never mind the details. These curves are basically just to show you that they're going down, which means that, so they're curves that essentially give you the loss functions that I showed earlier. So they're going down, so that's what they're supposed to do. So something is training here, so we get meaningful results. And so this is the actual main result. So this is the one mass that it turns out to be in the end. So this could be the top mass or the charm mass, if you want to think about it that way, as a function of one complex structure parameters. From the many complex structure parameters that exist in this model, we've just kept a one parameter family just for simplicity. And the black curve here is the actual full result from the full calculation, taking everything into account. So that should be sort of the correct result. The red curve is the result that you just get from these reference values, the Fubini study metric, if you will. So as you can see, this is actually surprisingly good. So you wouldn't maybe have guessed this, that if you, instead of taking the Ritchie flat metric on a Clavier, you just take the Fubini study metric from the ambient space and restrict it to the Clavier, that would be any good, but it's not bad. And this blue curve is when you do what is often done, which is to just assume that the kinetic terms of the fields are canonically normalized incorrectly, right? But it is often assumed. And then you get the blue line, which, as you can see, is pretty far away from the correct result. And so there are a few remarks here. Well, the fact we only have one mass here is because there was an additional symmetry that makes the two masses degenerate. So we can break that, and we've done this so we can go into other places in the complex structure moduli space and show that this degeneracy is broken, and we can get to some kind of hierarchy, which is not a bad start. Well, I said the red calculation is not bad, better than maybe you would have expected, but this blue result is clearly far off. So you shouldn't be using canonically normalized kinetic terms here. Okay, good. So this was, if you want, a proof of principle that this kind of calculation can be accomplished, but it's not realistic. So I want to go at least a little bit into the direction of trying to get a model that will actually give you the masses as we observe them. So for that, let me talk a little bit about the moduli space that we are considering. So this is meant to be a sketch of the bundle moduli space on a given Calabi-Yau manifold. This red line here is what I call the abelian locus. That is where the vector bundle is the sum of line bundles. So that's the locus that I've been working at so far. So that's where the bundle moduli, which I call little phi here, they are set to 0. Right? And that's also the locus where you have these extra U1 symmetries immediately appearing. And the reason why we find it hard to get realistic models on that locus, even though the calculation is easier there, is that there are these U1 symmetries, and they already introduce a pretty restrictive texture of your Yukawa couplings that's usually not compatible with, well, not even with 3 non-zero masses, as you've seen from the previous example. So what we want to do is we want to somehow go away from the red line and go into the interior of the moduli space. So one way to think about it is here on the red line, say you only have the up-Yukawa coupling and only those components that would happen to be invariant under those U1 symmetries. Once you go into the non-abelian part, so you switch on those vacuum expectation values for those little phi fields, then you can write down those operators here. Again, of course, as consistent with the U1 symmetries, but there are no more possibilities because you have these singlet insertions available to you. So you can think of this as some stringy version of Froggatt-Nielsen models, if you know what that is. So this is what I said. So realistic models on the red line are not very likely. We have two ways of improving on that. We could either try to do the full calculation that I just showed you at the non-abelian locus, but that's very hard, and we don't yet know how to do it, essentially because non-abelian bundles are harder. Or we could deform away from this red line by switching on the VEVs in the low energy theory of these bundle moduli phi. And so it's the latter thing that I want to talk about. It's the slightly lamer thing, but it's what we can do for the time being. So how does this work? So far we've looked at this. So we have Yukawa couplings at the abelian locus, which were functions of complex structure moduli. And now we make them functions of the bundle moduli, and in fact also functions of what I call big phi, which is e to the minus t. So this would correspond to incident corrections. And all these things are now constrained by these U1 symmetries. So there'll be certain monomials that you can write and others that you can't write as controlled by these U1 symmetries. And the U1 symmetries and their charges in turn, they are completely determined by the topology of your compactification. So for example, if you're writing it up quarks, they come from some harmonic form nu u, which comes from the first cohomology of a line bundle LA, where A goes from 1 to 5, then it means that the charge of this field is EA, where that's the 8th standard unit vector in R5. Right? So it's charged with +1 under the 8th U1 symmetry, uncharged under the others. And so that is completely determined by which cohomology this originates from. And these T fields, or the big phi fields, they also have some charge, which is essentially comes from the integers that define the line bundles. So again, this is essentially a string realization of a Frogat-Nielsen type model with many particles and multiple U1 symmetries. So we have this database of standard models. We only looked at a subset of those. We searched through this. We constructed all these operators within this Frogat-Nielsen setting, and we checked whether they can be made consistent with the observed masses and mixings in the standard model, at least at one particular point in moduli space. And from the few hundred or so models that we scanned, we found basically 2 examples where that's possible. This is one of them. It's this particular Calabi-Yau. It's an intersection of 2 polynomials in an ambient space of 5 P1s, again with a Z2 times Z2 symmetry, with a certain sum of 5 line bundles. This has exactly the MSSM spectrum. And if we pick the right point in our moduli space, which means an arbitrary choice at this point of little 5Fs and big 5Fs, then we can reproduce basically everything that we need to reproduce in terms of Yukawa couplings. So this is, of course, a preliminary story. We haven't done the full calculation for this model because we can't do the non-abelian calculation yet, but at least it shows that there's something there that can be found. Yeah, so this, to my knowledge, is the first proof of existence, if you will, that there's something that can be consistent with the observed masses of particles within string theory. At this point, it still is, yeah. But that needs to be broken eventually. Yes. No, supersymmetry needs to be broken. And it will be broken. But that's all part of the moduli sector. So this was the third of the 3 points that I said initially needs to be addressed, but I'm not going to address here. Yeah. But the fact is that the Yukawa couplings, the values of the Yukawa couplings, they do not depend terribly much on how you break supersymmetry. There's a bit of depending on how the running of the coupling goes, but that's not dramatic. Okay, so conclusions. So as I hopefully told you, calculating these Yukawa couplings in, at least in geometric string settings, is hard, essentially because you require the rigid flat metric and the related quantities for which analytic expressions are not known. And we've shown, at least for this restricted class of models, that you can compute these things numerically quite efficiently using machine learning techniques. I've shown you that this can, in fact, then all be combined to explicitly calculate these Yukawa couplings, at least for those models with abelian bundles. Unfortunately, the result for that case wasn't realistic yet, but I have shown you that by sort of studying these Fogart-Nielsen type models, by utilizing these U1 symmetries and using that to constrain the operators, you can make some progress and find, in fact, a few models which will have the right couplings. And well, there's many things to do. I mean, we would like to understand how to perform these computations for non-abelian bundles. That's more difficult. And of course, we need to understand this whole point about moduli stabilization, including supersymmetry breaking, of course. And the goal would be to finally then find a model where you stabilize the moduli at a place that will then also give you the correct Yukawa couplings when you insert into the calculated quantities on that side. So that's, of course, a dream, but at least we've come some way. So thanks very much.
Thanks, it's super interesting. The disagreement between the Fubini studi and the actual numerical value, does that persist for other? That was like one example you showed, but is that a generic feature? And if so, could you maybe do an initial scan, just, you know, eyeball it with the Fubini studi and then pin down in that corner?
Yeah, I think my feeling is that that is relatively generic, probably if you don't go to extreme points in the Calabi-Yau moduli space. So if you sort of make the Calabi-Yau too strange looking within your embedding space, then I would imagine that maybe the Fubini study metric isn't that good anymore. But you're right, this initial scan, just using that approximation is something that we have in mind doing, yeah.
String models with the properties you mentioned have been found, many of them have been found in the context of Gepner-Orient folds in the 90s. And in fact, in that case, the Fogart-Nielsen type of symmetries are natural because they are anomalous U1s and they can generate the hierarchies of the mass matrix, etc. Now, the question is, what kind of U1s are there that you're using in the heterotic case? Are they anomalous or not?
They are.
They are. Okay, thank you.
Yeah, I mean, otherwise, the gauge, we will struggle with the extra gauge bosons, right? So they're heavy.
Hello, I'm curious, what are the advantages of using machine learning techniques for solving the PDEs instead like of old-fashioned numerical?
Right. Yeah, okay, thanks. Yeah, so yeah, old-fashioned would be like grid-based methods. These are 6-dimensional spaces, right? So if you, suppose you picked 100 points in every direction, right? So that'd be 10 to the 12 points, right? So that's considerable. I've shown you on one of the earlier slides, we picked 300,000 points on the Calabi-Yau, and that's what we're training on. And that gives you rather good results. So it seems that's a clear advantage. The whole technicalities of meshing on the Calabi-Yau is, of course, just horrible in its own right, independently of the number of points. You don't need to do that here. All you need is a random sample of points that is distributed according to some distribution that you know, which in this case is a Fubini studi distribution, and that it's known how to do that.
So during your study with that specific loss function, did you find...
Can you speak up a little bit? Sorry.
Yeah. So did you find any problems with training the model regarding to local minima of the loss function?
You're asking, have we found the global minimum? Is that the question? We don't know. Right. So what we do know is that we compute some sort of measure of the accuracy, which is often called the sigma measure, which essentially is some integrated measure for how much the metric deviates from being Ritchie flat as you integrate over the manifold. And we know that that is small. Yeah, but of course that doesn't mean that you have to be in the global minimum. Yeah. So that's in fact an interesting question, and I think that's basically an open question to have some sort of mathematical framework by which you can decide. So essentially, you would have to probably go through Yau's proof. I mean, right, and sort of look at all the estimates very, very carefully, and then decide how far the neural network has to be, or how close it has to be. You know, what the error in the neural network can be, so you can actually conclude that the metric is nearby. Yeah, but that kind of precise mathematical analysis hasn't been made.
I'm just curious, can we gain some understanding of the hierarchy in the quark masses and, for example, CKM from this kind of calculation? Can we understand something about why that happens?
Yeah, I mean, maybe that's easier to understand in the second part that I talked about, right? So I think in physics there are basically two ways of getting a hierarchy. One is taking a smallish number to some power. The other one is e to the minus t. Right, and so this is what I talked about in the second one. The Froggatt-Nielsen method is essentially taking something smallish to some power, and what the power is controlled by the symmetries. Yeah, e to the minus t is a non-perturbative effect. So I think my understanding of where our hierarchy in the Yukawa couplings most likely comes from is probably a combination of those two effects.
Okay. Thank you.
Thanks.
We put this outside and we reconvene in 30 minutes.
All right. Hello, everybody. So I have some meta announcements to make, but I'll try to bring them to you in the form of a quiz. So who here, and this is a show of hands point, has heard of the life of a showgirl? Show of hands. Very good. So there are at least some young people in the audience. So that, of course, is the new Taylor Swift album that came out 2 weeks ago. So as you may be very well aware, if Taylor Swift had never existed and never had chosen to hold her New World Tour a year ago during when we actually would have had strings here, we would not be sitting here now. An important thing about Taylor Swift, so this is going to be a mnemonic device, is she's born 1989, like many fine other people, in December though. So it makes it almost 1990, which happens to be the very door code which we can use to open the door. But due to some old school reasons, you can actually use the thing, you have to use the button device. So not the thing with some touch pad or whatever. And yes, we have to use the code due to some trust issues, which we can go into perhaps at some later point. All right, without further ado, I give the floor to the chairperson.
Okay, thanks. So we'll start the second part of the morning session with a talk by Lorenz Eberhardt, and he's going to evaluate one-loop string amplitudes.
Right. Thanks a lot to the organizers. Thanks for organizing this very nice conference and inviting me to give a talk. And indeed, I want to talk about some recent progress that we made in actually getting numbers, similar in spirit to the previous talks from string theory, and actually evaluating one-loop string amplitudes. And this talk is based on a collaboration with many fantastic people. So my student Marco Baccianti, Jivan Chandra and Tom Hartman at Cornell, and Sebastian Misera. So first, I want to start off with this general message that unless maybe you thought about it or you work in the area, maybe you're surprised that it's actually quite hard to compute string amplitudes. You usually get told in your string theory course that it's beautiful, and then everyone writes down the Virasoro-Shapiro amplitude or the Veneziano amplitude and tells you how beautiful it is. But then if you look at higher loops or more general settings, it very quickly becomes much harder than field theory amplitudes, let's say. But let's nevertheless start at this very nice Virasoro-Shapiro amplitude that we all love. So this is describing the 2-to-2 scattering amplitudes of gravitons. And I'll just talk about type 2 strings in this talk. It doesn't really matter whether it's type 2A or type 2B. And at tree level, you get this nice amplitude. So there's this tensor factor in front that has all the polarizations of the 4 gravitons in it. It's some tensorial structure that doesn't really matter for the rest of the talk because it's fully fixed by supersymmetry. So this will be the same at every loop order. And the really interesting thing is the function that is sitting here. So it's some function of the 2 Mandelstam variables, S and T. And we know that at tree level it takes this very beautiful form in terms of gamma functions. And so let me just point out some of the nice features. So it's manifestly crossing symmetric. So you see it's symmetric in S, T, and U. And it has this feature of dual resonance, where by putting in one series of poles in one channel, you automatically get the other series of poles. It is Regge bounded. It is UV soft in a sense that we'll also discuss later. Basically, if you increase the energy, but you keep the angle, the scattering angle fixed, the amplitude goes down exponentially fast. And of course, it's also consistent with unitarity. Okay, and it's analytic and all the nice things. And basically, I'm sure you're all aware, but basically this formula was guessed before string theory was around. So this is how the subject started. So today I want to basically learn similar things about the one loop amplitude. And for that, I'll show you one general method that you can use to evaluate one-loop string amplitudes. But it's really maybe more appropriately titled How to Compute Integrals over the moduli space of the torus. Because you can also use that for other integrals that you might encounter. And to show you a little bit of what kind of results you will get is that if you try to compute now the type 2 one-loop amplitude, so this is flat space, 10 dimensions, no compactification, and at some fixed scattering angle, here I randomly chose 60-degree scattering angle, and then we can evaluate this amplitude. It doesn't have a very nice closed form formula as on the previous slide, but we still can evaluate it numerically. And you get a curve like this. So what are you looking at? You're looking at the energy on the x-axis. I put alpha prime to 4, just so that all the mass levels, so all the mass squares in this normalization are all the integers. And because of that, I'm also multiplying by the sine pi s squared, the amplitude, because otherwise I will get poles, or actually double poles at one loop on all the integers, and it will be an ugly plot. So I'll just multiply by this factor sine pi s squared, so I get nice plots, and nothing too special happens on the integers. And what I'm also doing is I'm taking an absolute value squared, and I'm plotting the imaginary part and the real part separately. And we're computing those in a quite different way. So the imaginary part will be much simpler. And it's notice that it's a logarithmic scale. So as I increase the energy, the amplitude drops down exponentially, just like the tree level amplitude does. And the yellow curve that looks a little bit more messy is the real part. And it has the same feature that it drops down exponentially. There's also this dashed line here, which is a certain prediction by Gross and Mende that we'll come to later, and that predicts this exponential fall-off. Should also mention that down here, you're basically talking about effective field theory. So as soon as you're sitting comfortably below the first massive mass level of string theory, you're basically having supergravity with various alpha prime corrections. And there is a huge amount of literature where people compute this alpha prime corrections, and so there's an alpha prime expansion, I think, to 7th order of the amplitude in the literature that you can find. And if you just plot that prediction, it's the blue and the yellow curve. You see that our way of computing kind of becomes much worse here. So we're kind of connecting with this, but we're actually not very good in going all the way to low energy for reasons that I'll explain later. Okay, so this is more or less what we'll be able to say. And now I want to tell you how to get to this kind of results. And I'll start by telling you how string amplitudes are defined. So there are certain integrals over moduli space, but with certain caveats that I want to tell you about. And then I'll tell you about the main way we evaluate these kind of integrals, which is via a procedure that comes from analytic number theory, developed in the 1940s by Rademacher, Hardy-Littlewood, and other people. And lastly, I want to talk about this high energy limit where there's this Gross-Mende behavior. So let's get started. If you read the textbook on string theory, then they will tell you something like this, that the amplitude at genus G with n points, so it will be some function of the momenta, and it's computed by computing a certain correlation function in the conformal field theory and integrating it over the moduli space of Riemann surfaces. So there are certain, so this is, it depends of course a little bit if you're talking about tachyons or gravitons or superstrings or what kind of string theory, but roughly the structure is this kind of integrals. One thing that I want to point out is that when you write these kind of integrals, they're usually never convergent. So they're kind of formula integrals. And the reason is a very physical one, because if you would integrate such a thing over a moduli space, let's say these are always finite and real quantities, you could never produce physical features in the amplitude, like poles and branch cuts, and the amplitudes has certain imaginary parts, and so forth. And they come because these integrals are not literally convergent. And they come basically because there's these boundaries of moduli space, and all the IR singularities, which are these physical features in the amplitudes, they arise from regions in moduli space near the boundary. And And there are several resolutions to this that have been employed in the literature, how to make sense of these kind of integrals. And the one that I like and I want to use is the following, is one explanation why this happens is because usually when we discuss string theory, we treat the worldsheet as being fully Euclidean. So we very much like our 2D CFTs to be Euclidean because we can use complex analysis and so on. But at the end of the day, of course, it's not Euclidean. It's a worldsheet that starts its life as a Lorentzian worldsheet. And so really what we should be doing is to integrate over something like a Lorentzian moduli space of surfaces. And one way to implement this is to modify the integration contour. So instead of integrating over the moduli space of surfaces, you first complexify this moduli space, which sometimes is confusing because the moduli space itself may or may not be complex. So if you're thinking about closed string theory, it is already complex. So forget that it was complex. Now you complexify it again, and then you define some contour in this moduli space. And this contour basically on most of the moduli space, it looks the same. But if you go close to the boundary of moduli space, you modify the contour. How do you modify it? Well, the moduli, of course, if you're close to the boundary, you're talking about IR, you're talking about low energy. So you're close to field theory, and one of the moduli becomes the Schwinger parameter in field theory, so which is the proper length of the world lines, and you're just Wick rotating it to a Lorentzian proper length. And that means something on the level of the moduli, and it defines you this contour. So there's a certain way to define this contour, and you can think of it as a version of the I epsilon prescription, because of course in field theory you're having the I epsilon prescription, but you also need to implement that in string theory. And once you modify the contour in this way, all the integrals are absolutely convergent. So this is a convergent way of defining string amplitudes. Okay, and it was popularized by Witten around 2013. Okay, so what does it mean more concretely? Let's get to our one loop string amplitude. And the expression is well known. You can find it in Green-Schwarz. And it's an integral over the moduli space of tori. So the tori I labeled by a modular parameter tau. It's also an integral over the locations of the vertex operators on the torus. So there are 4 vertex operators. In principle, we need to integrate over all 4. But because the torus has a symmetry, we can use that translation symmetry of the torus to fix one vertex operator to one position that we like, and we only have to integrate over 3 of them. And then there's an integrand, and the integrand is given by pretty simple theta functions. These are just Jacobi theta functions. And it's modular invariant and so on, it's all nice. So it's a seemingly very straightforward integral. But it turns out that doing this integral is very, very hard. And basically all the methods that you know from field theory, they're pretty hard to apply in this case. One thing that I want to tell you is what this contour gamma means. So this is this modified contour. Usually people tell you, well, integrate over the fundamental domain of the torus. And the fundamental domain is basically is this keyhole region. So it's tau between -1/2 and the real part of tau between -1/2 and 1/2, and the absolute value of tau bigger than 1. And this is fine for everything down here because you're in the UV region. But once you go up there, the torus becomes very long and thin, and you're going to approximate field theory if you want. If you don't look very precisely, you might think you have a word line, and you need to Wick rotate your Schwinger parameter. What that means concretely is that sort of the fundamental domain is kind of rotated because you're complexifying that space. So again, forget that tau was complex. Complexify it again, you will get a 2-dimensional complex space. And you can say, well, one of the directions is real part of x and real part of y, where tau is x plus iy. But now this integration contour is folded in the region, in the imaginary part of y region. So you take the real part and the imaginary part of tau, and you complexify them again. And you get this kind of 3-dimensional contour. Okay, so, and once you integrate over this, everything will be convergent because basically everything here along this direction are phases, they're just oscillating, and then this 1 over im tau to the 5 makes it such that it's convergent in the end. Okay, so this is a well-defined integral, but because everything is oscillating now and so on, it's still very hard to put this on a computer and just integrate numerically. It's terrible. And also we are already seeing that the amplitude actually exponentially goes down, but if you look at the integrand, it goes exponentially up. So there's an exponential amount of cancellation, so putting it on a computer is terrible. Okay, so how do we evaluate it? So that's what I just said. It's convergent, but it's terrible for, say, numerical evaluation because the integrand is very highly oscillatory. So what we want to do is to do further contour manipulations, because now we're in the realm of having a contour in some complex space, and the integrand is holomorphic in the sense that it's holomorphic in the complexification of the moduli space. It's a holomorphic function x and y, where x is the real part of tau and y is the imaginary part of tau. And so we can do contour deformations. So let's first do the easier part, and let's first compute the imaginary part of the amplitude. So the imaginary part of the amplitude fully comes from the region where the integral, the contour folds in this region, because the integrand is real, and so it's real for the usual moduli. So this part of the integral will only give real results. So if you want to compute the imaginary part of the amplitude, it's quite simple. You just have to take the difference of the two I epsilon prescriptions. So if you fold the contour in this direction, you used one sign of the I epsilon prescription. If you fold it in the other direction, so going into the slide, you have the other sign of the I epsilon prescription, and the difference gives you the imaginary part. And so the imaginary part is this contour that kind of only goes now through the slide. And the magic about this contour is that all the kind of complications that have to do with how the fundamental domain exactly looks like, they don't matter. And in fact, you can evaluate the integral over this contour by just knowing the local behavior of the integrand near infinity, because the height where you turn left or right doesn't matter. It's a contour deformation. So you can push the contour up all the way to infinity and just pick out, just know about the local behavior of the integrand there. So let me show you how that works in a simpler example. But it's the same idea, but just so you see what happens. And let's compute something that you also usually told you shouldn't compute, namely the one-loop amplitude in bosonic string theory, or one-loop partition function. So it's this expression where eta is the Dedekind eta function. And usually you get told it's not convergent. Yes, it's not convergent, but once you change the contour, it is convergent. And the one-loop partition function of bosonic strings perfectly makes sense, but it's not real, which also makes sense because it's unstable. So if you compute a determinant, one-loop determinant or something, there will be some negative modes, and the imaginary part of this partition function just tell you about the decay rate of the vacuum. Okay, so let's compute it. Let's compute the imaginary part. So it's given by this difference of the two contours. Let me call it gamma imaginary. And so now in this gamma imaginary, what we said is, well, is this contour that goes into the slide, and I can push it all the way up to infinity, so I can make my im tau as large as I want. What that means is that while this 1 over eta to the 24 has some expansion, sorry, the sign is wrong here. That's kind of important. This is supposed to be a plus. So this is the piece that is growing that usually you get told doesn't makes the integral divergent. And then there's like 24, and then there are subleading pieces. And now you see that all the subleading pieces, they will die out as you take im tau to infinity, because the subleading pieces actually have minuses in the exponential. And so you can just omit them. And that should make sense to you physically, because they will not contribute to the decay rate. The only thing that will contribute to the decay rate is the tachyon in the bosonic string. And so it's exact to just omit them and just have this integral where I call im tau y, and again, this is supposed to be a plus sign. And then the imaginary part contour is just this contour that goes from 1 minus I infinity to 1 plus I infinity in the imaginary part of tau. And the 1 is arbitrary, it could be 17. And it's some Hankel contour, whatever, you just evaluate it in some number. So it's easy to evaluate. Very good. So this is the idea, and you just apply it to the full amplitude, and you get some answer. It's exactly the same logic. And the structure is as follows. Well, you get the imaginary part will be given by a sum, a finite sum over masses. And these are all the masses. So this answer is basically given to you by the structure of unitarity cuts in a quantum field theory. If you compute the imaginary part of a quantum field theory amplitude, it's a sum of all possible unitarity cuts that you can perform on the amplitude. So which means that you can exchange some massive particle here and some massive particle down here, but the mass has to be such that you have enough energy in the amplitude to actually produce it. And so this is why this inequality is there, some kinematical inequality. And the sum over masses is just the sum. This is in the derivation. This is the constraint that the corresponding term in the expansion of the integrand is actually divergent as you approach the cusp. So in technical terms, these are sometimes called polar terms. And then, well, you can do some of the integrals and some are left over. And after all the dust settles, you get one sort of Virasoro-Shapiro amplitude here, one Virasoro-Shapiro amplitude for this part, and you get some kinematical factors. So this is a Gram determinant because you have to integrate over the on-shell phase space. And then there's some polarization sum because this is massive exchanges. So there's a huge amount of sum over polarizations. And if you would do this in field theory, it becomes massively complicated very quickly because you have to construct all the massive string states and compute the polarization sums and so on. But if you just extract it from the one loop amplitude, it's kind of straightforward, and it gives you some polynomials, and they are represented in terms of some generating function and so on. And it's a squared because it's the square of the answer that appears in the open string. Okay, so this is the structure. And this, if you implement this on a computer, you can pretty quickly get this blue curve. So it's not trivial to implement, but it's also not very hard. And you need to do still two integrals. So you saw, if I could just go back, there's still two integrals because of this integral over the on-shell phase space. But these integrals are completely convergent. There's nothing bad in them. And you see in this representation, all the physical features have been made manifest because you get a sum, finite sum, and if you increase S, you can get new terms. These are the discontinuities and the branch cuts that are in the amplitude, and also the poles in S, they're manifest in these gamma functions. So all these singularities that you do expect, they're already there. Okay, and so that gives you this blue curve. But now what do you do for the real part? Because that's really the thing that you could say, it's the new thing that you cannot get just from the optical theorem, say. And you would expect this much more complicated. And there the idea is that you sort of recycle the computation for the imaginary part, but infinitely many times. So let me tell you what this means. Let me first tell you what happens for the open string, because it's easier to draw pictures. So for your open string, you have to similarly compute an integral, but it's only integral over tau holomorphically, but not d squared tau. So it's a one-dimensional integral. And roughly speaking, you have to compute a one-dimensional integral, turns out to go from 0 to 1/2, but that's not really important, over the modular parameter of some modular object. Okay, that's the integrand. And what you do is to do a sequence of contour deformations. And this was the sequence that was invented by Rademacher in the context of analytic number theory. So what you do is you draw all these funny circles. They're called Ford circles. Their radius is something like 1 over twice the denominator squared, and they touch the real axis at all these irreducible fractions. And they give this very nice pattern that they all touch, but never overlap. And the original contour is this one that goes from 0 to 1/2. And you see what you can do in the nth step of this deformation is that you take the contour that goes around the circles whose denominator is at most n. So meaning in the fifth step, let's say you go up to the circle C1/5, you go around the C1/5 until you hit the C1/4, you go around the C1/4 until you hit the C1/3, you go around that until you hit the C2/5, take the C2/5, and you go around C1/2 until you're there. That's clearly contour deformation from there to there. And then what you can do is you can cross your fingers and you can take n to infinity, and you hope that everything will converge. Because in the limit n to infinity, you get a contour that goes around all the circles exactly once. You can see here you're already going around the C1/2 almost entirely. If you make this denominator bigger and bigger and bigger, you will sort of, this contour will be more and more complicated. And in the limit, you get all the circles. And So this was applied, this technique, to the open string in these 2 papers. And why is this helpful? Because once you have integrals around circles, well, a circle around some fraction that real axis by modular transformation is the same as an integral over a horizontal line. Just apply a suitable modular transformation. For example, the integral over the circle near 0, if you take tau to -1 over tau, is the same as an integral over a horizontal line. And it's actually exactly the same computation as we just did for the imaginary part. This is exactly the same contour as before. So this means that once you do this, and provided it converges, you get something where every step of the computation looks very similar to the imaginary part. There will be some additional phases and stuff, but essentially that's what it is. Okay, so if you do this again for the toy example, because the real thing is kind of a complicated computation, so you want to compute the real part of this, then you hit the additional problematic thing is that this is now an integral over the fundamental region. This is not exactly what we discussed in the previous slide. But you would still hope that you can somehow compute this by knowing all the singularities of the integrand. So what you essentially need is a 2-dimensional version of this Rademacher expansion. I should say also that in the literature there are many ways to approach this that compute this integral. So here are some. Hopefully I didn't, there are probably more. But if you do it in this Rademacher way, it turns out that you can do it, but it took us a while to figure out, and we needed the help of these people in Cornell. So there is a version, and this basically holds for any modular function. There's some boundedness condition that if you compute this integral over the fundamental region, well, really this kind of Lorentzian version of the fundamental region, and you want to know the real part, because the imaginary part is easy, you can express this as an infinite sum over a contour integral, this is now in tau and tau tilde, of the same function. And this contour integral grows around the same 4 circles in, say, tau tilde, but over the horizontal line in tau. So there's a modular transformation, so this thing is modular invariant, and they're simultaneously transforming tau and tau tilde, where tau tilde, I'm calling tau tilde minus tau bar, so that tau tilde is also in the upper half plane. Yeah, the main point is that this is a sum over all these kind of 4 circles, and there's some additional factor that doesn't really matter, but technically it's there. And there's some kind of analytic number theory magic of some Dedekind sums and so on. You don't really have to worry about it. The main point is that you can write this integral as a sum, and all these integrals will be easy to evaluate, because again, you can push, like horizontal integrals, you can push them towards a cusp. And similarly, if you have these circles, you can make the circles as small as you want. You can shrink them as small as you want, and you only need to know about the singular pieces of the integrand near these circles. And the proof of this is follows from doing many contour manipulations and so on that you can read in the paper if you really want to. It's kind of fun. Okay, so just to convince you that this works, let me tell you the answer for the bosonic one-loop partition function. So if you want to compute this integral, you can do it. It will be an infinite sum representation. And so there's an absolutely convergent representation with some phases. So you see you get this e to the 2 pi I a over c, and you also get a star over c, where a star is the inverse of a modulo c. These are objects that very frequently appear in this Rademacher story. And you also get these Bessel functions, which are also very typical here. And you can very quickly, you can put this on a computer. It's very easy to implement, and it gives you very good approximations quickly if you cut off the sum, say. And again, the imaginary part we already computed on previous slides. It was easy. And I just want to emphasize that this way of computing integrals over the fundamental domain, it's not really special to string amplitudes. It works for any modular invariant function, provided it satisfies a certain boundedness condition, and this boundedness condition translates to the fact that the sum has to converge absolutely. Roughly speaking, that is analogous, if you're familiar with the usual Rademacher expansion, it's analogous to the fact that the modular weight of the object that you're integrating has to be negative. So, okay, so this is the technology that we want to employ now. So we want to apply this, but now where the integrand is the actual string amplitude. So it's a some modular invariant object. And if you do this, you get kind of a mess, but you get a mess that is still much easier than the thing that you started with. And if you apply to the full string amplitude, well, you also have to worry about the other integrals. You might, I sneakily only talked about the tau integral, but of course there are also the integrals over the other vertex operators, but they're kind of slightly easier, but they also contribute and they will make the sum bigger. So there's a sum over these fractions that come from this Rademacher expansion, but there's also a sum over certain winding numbers that come from this Z integral. But the main point is that you will get some kind of pieces of the answer. Those pieces are similar to evaluate to the imaginary part. So they have this, this unitarity cut of way of writing them with additional phases. And once you sum everything up and it turns out to converge, you get the full amplitude. Okay, so when is this good? Well, so still admittedly it's still hard because you still have to compute a very big sum. And every piece in the sum is also not terribly easy. So first of all, you might worry whether it's convergent. And the answer turns out to be probably it is. We cannot prove it. It seems to be convergent, but not absolutely so. But it at least numerically converges pretty fast. And it's practical for a region where S is not too small and not too big. The reason why it shouldn't be too small is if you take the Mandelstam variables to 0, the convergence actually becomes worse and worse and worse. Because we're, and the reason is because while this representation makes most of the analytic features manifest, there's one feature it does not make manifest, namely the massless branch cut in the amplitude. So there's the kind of massless branch cut that you also have in supergravity. And that is manifested in this formula because the sum starts to diverge. And so that's much harder. That's why it's actually kind of, ironically, kind of hard to go to low energies. It's also kind of hard to go to very high energies because there's a sum of polarizations involved in all this, even the imaginary part, and the sum kind of becomes more and more wide if you go up in energy. And so numerically, we can push to pretty high orders. It depends a little bit. If we compute the full amplitude, it's roughly order 10. If we compute some pieces like mass shifts and so on, we can go higher, but that's roughly what we can do. Although one thing I should point out is that I've been mostly complaining about this kind of cancellation if you do the direct numerical integration, which happens at large S. For small s, it's not really a problem. You can just directly integrate the amplitude and you get pretty good results. And of course, there's alpha prime expansion. Okay, so this is mostly the methodology. Let's look at some of the results. And let me first start with this in the forward limit. So now you make the scattering angle 0, and you plot the amplitude as a function of the energy. This is a pretty different looking plot than what we had in the beginning, where we had a scattering angle of 60 degrees. And in particular, it's not a logarithmic plot. It's a linear plot. And I'm also not taking absolute values because linear. I'm multiplying by S just to make it slightly nicer. And what you see is that the amplitude is kind of oscillating, and it's kind of order 1. Right? It's not really growing or becoming smaller, so it's of order 1 over S. And this is what you expect, because this follows from redshift physics. So there's a prediction from Amati, Cefaloni, Veneziano. There's also direct integration from Sundborg, which gives you the asymptotics of this, this formula. And we know actually that the asymptotic is purely imaginary. So the blue curves eventually wins over the yellow curve, which is not completely obvious from the numerics. And the reason is because the arrow is of order 1 over log S. So you have to go to ridiculously high energies. And you see convergence to this asymptotic result is actually rather poor. So that's maybe slightly discouraging. But sorry, for some reason I went back. That's the reason. But if you look at fixed angle scattering, it turns out that you actually much quicker go to asymptotics, which is this Gross-Mende asymptotics. So this is the same plot as in the beginning. Let me not tell you again the same things. But how does this Gross-Mende asymptotics work? It works, and I should be quick about this. by noticing that if you have an integral, so the integrand for a 2-to-2 scattering in string theory is always of this form. So it's an integral over moduli space, some functions, and importantly, there's a function raised to the minus s and a function raised to the minus t. So that's always the structure. And you see that if you go to high energies, so you make s and t really large, then this integral will be dominated from a special region moduli space, because you can do a saddle point approximation on this integrand. And so this integral is approximately sum over saddles of this form, and you have to, there's some one loop determinant and so forth. So this is the argument of Gross and Mende, and they also tell you which saddle they think will be dominating at some genus G. And essentially they have some special saddle that they can construct. So at tree level it's easy, you just solve the saddle point equations. On the integrand it tells you that the cross ratio is pinned to some specific value. At higher loops it becomes much more complicated, and the saddle that they tell you that is always there is that you can construct a particular Riemann surface as a G+1 fold cover of the sphere that is branched over 4 points, and those 4 points are exactly the ones where you insert the vertex operators. Let me just tell you what this means from the space-time point of view, because I think it's kind of interesting. When we think about string scattering, we have some string going in, string going out, and then we usually draw some kind of holes in it for higher genus. But actually the saddle point at high energies, it is just the same as the tree-level scattering, but just the same worldsheet G+1 times on top of each other. Just take the worldsheet in target space, take G+1 copies, cut it open and reconnect it in different ways. Formally, from the worldsheet, that looks like a higher genus surface. But from target space, it just looks like a worldsheet that does that. So it's kind of funny that it's kind of fake higher genus, if you want. Okay, and there's a bunch of challenges and problems with Gross and Mende that let me not go too much into. But the only thing I want to mention is that because the integration contour goes over this complex modular space rather than the real one, in our way of thinking, there might be other saddles than the Gross-Mende saddles that are actually outside of the real modular space, but are on this complexified modular space. And also, it's pretty hard to compute their multiplicities. So what we did is just brute force. We computed the amplitude because we know how to evaluate it, and we compare. And if you compare the explicit data, and what I did here, you see now S goes much higher than it did previously, but I'm only computing the amplitude on integers, because on integers it's much easier to evaluate because it's computing the decay width. Because remember, at integers, the amplitude has double poles, and the residues of these double poles are the decay width of particles, and they're technically much simpler to evaluate. So we can push it much further. And if you just compute them, you get this curve. And this is, again, at some fixed angle, 90 degrees this time. They're normalized in some particular way. This is the scaling that Gross and Mende predict you. And if you include all the factors and so on, Gross and Mende actually would predict you this red curve. So it's not terrible, like given that this we're multiplying by some exponential factor and so on, but it's also not quite there. So one thing that you can, first of all, what I did is to include also the sub-leading correction from Gross-Mende. This is why this is not a straight line, but it doesn't really matter. But one thing that you see is, first of all, the multiplicity of the Gross-Mende saddle should not be 1. Turns out it needs to be 3 to match with the actual data. So the Gross-Mende saddle appears 3 times in the contour. And the other thing that you notice is because there are these weird oscillations, they actually come from these other saddles that are not in the real part of modular space, but are in the complexified modular space. We understand what these saddles are. We don't understand how to compute their multiplicities. So all we can do at the moment is we have this data, and we can tune the multiplicities such that the data fits pretty perfectly on the saddle point evaluation. Notice again, this is true for large S, so the fact that this doesn't match here is not a problem. And so this is the imaginary part. We can also do it with the real part. So the real part, from Gross-Mende prediction, the real part asymptotically is actually 0, because the one loop, the saddle point approximation around the Gross-Mende saddle is purely imaginary. But it's actually not 0. It's of the same order of magnitude as the imaginary part, and it's again oscillating and comes from these Lorentzian types of saddle. Okay, I'm really out of time, so let me just very quickly give a summary. So these contour deformation tools are very useful for string amplitudes, and for other things, of course, also. So in particular, they're numerically useful if you want to actually plot the amplitude and get numbers out and so on. And they allow us to probe the physics of this amplitude much further. To evaluate the amplitude, the important feature was that this Rademacher way of computing it only needs the behavior of the integrand near the cusps. So we actually never had to input what the integrand at the generic point in moduli space is. We can get the answer from just knowing what happens near the boundaries of moduli space. And also these representations make a lot of analytic structure manifest, and in particular they also make contact with this Grosse-Mende limit, and the development that is still in progress is to how to figure out exactly what the multiplicities of these Grosse-Mende saddles have to be in order to actually match with the amplitude. So thank you very much.
Yeah, thank you. Questions, Elias?
I have two questions. What controls the convergence of the Rademacher expansion sum that you had of the functions? And also, can you calculate the asymptotic form of the decay widths for high energy string states?
Thank you. So first question, let me get some backup slides. Okay, so this is the rough form of the answer. And the devil sits in these phases. And the phases basically are controlled by, they're more oscillating the higher the energy goes. So all these phases are exponential of s times something. And so if you make s bigger and bigger, there are more oscillations and tend to be more cancellations. That's why converges faster, at least numerically. Whereas if you let s go to 0, then all these phases go to 1 and convergence breaks down. That was the first question. Second question was if I can get asymptotic formulas for decay width. Not from these formulas, unfortunately, because what turns out to be very hard to control are these sum over these intermediate masses and these polarization sums and so on. So at the moment, we're evaluating this numerically and comparing to Grosse-Mende, which we can compute analytically up to the saddle multiplicities. So, and those we are fitting.
All right. Yeah, I also have two questions. The first one is when you compare to Grosse-Mende, you looked at integers. That seems very particular. Did you also check other values? Because maybe you said that already.
No, I did not. So thanks. So we did check with other values, but it's just a numerical problem at this point. It's much harder to compute the amplitude at generic values than at these integers. It does match. There are also they're also on top of what I mentioned. These multiplicities can be like trigonometric functions, basically, because there are saddles where if you say take Z1 around Z2, but you're not doing that with Z2 bar around Z1 bar, you get additional phases and they can resum in trigonometric function. This actually happens at tree level. And so also those trigonometric functions you have to guess, but we make some guess that works. So
I could imagine that the factor of 3 was just due to picking particular points, but you sort of checked.
Yeah, we check at other points as well. And actually, if you look at the amplitude, it's very important to check these other points because the amplitude tends to oscillate roughly. I mean, there's this kind of oscillation, but then there's also faster oscillations that you can see in the plots that are roughly period 1. So it actually goes up and down period 1, and they come from this other trigonometric function.
Second one was these sums, the Rademacher sums. Do you have any intuition for what they mean?
No, it's a kind of a magic. In particular, you see it fails exactly for field theory. That's kind of the, if you want annoying or exciting, depends on your perspective thing, that they only work for string theory amplitude. They do not work for field theory amplitude. So it's kind of a stringy magic. And in particular, if you show this to field theorists, they're kind of, it's very peculiar that you have like unitarity cut representations or almost unitarity cuts with additional phases for the real part of a one loop amplitude. That's a thing that shouldn't work, but yeah. Thank you.
It's like this. Yeah. Okay, and the last speaker in the morning session is Yolanda Lozano, and she's going to tell us about ADS352 and defect CFTs.
Yeah, first, see. Okay. Okay, thank you very much for putting together this fantastic conference and for giving me the opportunity to present my results here. So I'm going to discuss some aspects of ADS3 CFT2 holography in connection with the description of defect conformal field theories. So you know very well that low-dimensional holography has always played a very important role in the description of black holes. More recently, it has also been used to describe conformal defects. What we mean by conformal defects, we mean defects that are inserted in some superconformal field theory with higher dimensionality in a way in which some subgroup of this superconformal group still remains. So we expect to have a lower dimensional ADS geometry that will be describing this defect CFT geometrically through holography, and then we can use it, especially if we are interested in learning about the strongly interacting regime of this defect CFT. So this is the idea. In string theory, these defect conformal field theories are typically engineered in terms of brane intersections in which one can talk about two different types of branes. One can talk about what we refer as background branes. These are the branes where the CFT, where the defects are inserted, live. But then we have another bunch of branes that we refer as defect branes, such that when they are added to the previous brane intersection, we have a lower dimensional field theory living in the whole intersection of both background and defect branes, and there is where the defect CFT will live. So when one takes the near horizon limit of this brane intersection, including defect and background branes, what one finds is a low-dimensional ADS space. Low, I mean, compared to the dimensionality of the ADS space that you would get in the near horizon limit with just the background branes. You get a lower dimensional one, which contains a non-compact internal direction. This is the presence of the defect branes by the reasons I'm going to mention now. In many cases, and I will see some examples of this, what happens is that this non-compact direction that appears in the internal manifold asymptotically, typically when it is sent to infinity, will become, with some other parts of the internal space, part of the higher dimensional ADS space that is dual to the background conformal field theory where the defects are inserted. This happens asymptotically locally. With this, I mean that this higher dimensional ADS space that appears asymptotically will have corrections both in the metric, but especially in the fluxes, because this will sign the presence of the extra defect branes. And this will be subleading corrections in this limit. So since you are familiar with RG flows, let me say that when you find this ADS, higher dimensional ADS space emerging asymptotically, this is different from an RG flow. Here, in an RG flow, you would have a higher dimensional ADS space in the UV, a lower dimensional ADS space in the IR. In the middle, you don't have an ADS geometry. Here, we are going to discuss ADS geometries with an internal, with a non-compact direction, which are ADS all the time, and only asymptotically in the UV will give rise to a higher dimensional ADS space. Okay, this is not an RG flow. So, oops. Okay, we are saying that we have this non-compact direction in the internal space, which hints at an interpretation of the solutions in terms of describing defects. Well, when you go and try to construct which is the dual CFT associated to this ADS space with a non-compact direction, you will find that it is ill-defined. But the way this is interpreted is by the need to complete this CFT when you are away from the defects with the higher dimensional CFT where the defects are inserted. So this is how you make sense of the presence of this non-compact direction. So in recent years, some low-dimensional ADS solutions have been proposed as dual to defect CFTs. And in some of these realizations, one can even see very explicitly how the CFT is described by some quiver diagram, quiver picture, and this shows very pictorially that your quiver is the result of inserting the defect brains inside the quiver that would describe only the higher dimensional CFT. I will provide a couple of examples of these explicit realizations. So the focus of my talk will be on the CFT interpretation of some ADS solutions, in particular ADS3, to massive type 2A supergravity and their possible relation to conformal defects. So this is based on some recent works last year with Neal McPherson, Nicolo Petri, and Nayeli Ramirez, who is in the audience. You can ask her further. Andrea Conti is now my student in Oviedo, and he's also in the audience. Giuseppe Di Viteto, Nicolo, and Nayeli, and now some work in progress with Andrea and with Chris Rosen in Crete. So which kind of ADS spaces, ADS3, as I already mentioned, we will be discussing? Well, you know that when you want to classify low-dimensional ADS spaces, this becomes quite challenging because the large dimensionality of the internal space allows for so many possibilities for the geometries, the topologies, and thereof the supersymmetries. So in ADS3, there have been complete or partial classifications with different numbers of supersymmetries by a lot of people. Here, I'm going to be interested mainly in some recent classification of ADS3 solutions that preserve 0.5 or 0.6 supersymmetries that were constructed by McPherson and Ramirez a couple of years ago. I will mostly be concerned with this 0.6 case. So let me be more concrete and give you the outline of the talk. I will start discussing this class of solutions because in the spirit of what I was telling you before of defect CFTs, this class of solutions contains a non-compact direction, and we will find an interpretation for them in terms of describing surface defects within the ABJM, or rather the ABJ extension of ABJM. Then more briefly, depending on the time that I have, I will discuss another class of solutions that we constructed some years ago, which are solutions also to massive 2A supergravity. These preserve a less exotic supersymmetry, 0.4, and we will try to interpret them as describing surface defects within 6-dimensional 1,0 CFT. In fact, this was our intention, but eventually we ended up interpreting them as describing the constructed 6D 1,0 CFTs for reasons I will explain. So let me start with the main example that I will be discussing, which are these ADS3 solutions to massive 2A with 0,6 supersymmetry, and their interpretation in terms of defects, surface defects in ABJM. So these solutions, as I said, were constructed by McPherson and Ramirez. They are ADS3 times CP3 foliations on an interval. They preserve 0,6 supersymmetry with an OSP 6,2 superconformal group, which means have SO6 R symmetry, which is realized geometrically on the CP3. I'm going to argue that these solutions can be regarded as an extension of ABJM to the massive case, that is adding extra D8 branes, which have the effect of turning one of the external directions of the ADS4 part of the geometry into an NAE scale using field theory language and generating a flow towards an ADS3 space. I will be more clear about what I mean with this claim. So the form of the solutions is very compact and neat. You find in the metric the ADS3 part, the CP3, and then you have the interval that is parameterized by this R. And the solutions are labeled by this function H, which depends on R and its first and second derivatives. Then you have a running dilaton. You have a Neves-Schwarz-2 form that is proportional to the Keller form of the CP3. And here I'm writing this L, which is an integer number, because having R being non-compact, these R, as you move in the R direction, you are abandon the fundamental region where the B2 has to lie in order to not be overcounting case equivalent configurations in string theory. And this forces you to divide R in intervals in the units that I have L, L plus 1. And in each of these intervals, you need to perform a large Gauge transformation of parameter L to enforce that B2 is in the fundamental region. This creates NS5 branes at these positions. At these positions, R equal L. So we have NS5 branes, and here I'm not bothering you with the details of the Ramon-Ramon fluxes, but we have all of them switched on. So when you integrate them over the non-trivial cycles of the CP3, you will find the 2, the 4, the 6, and the 8 brane charges. So this is the whole plethora of branes that are involved in these solutions. So this function H, I was saying, this labels the solution. This satisfies a Bianchi identity in terms of its third derivative and proportional to the Romance mass. So this means that the most general solutions that you can construct globally, you can do it gluing local solutions with the 8 branes. You take F0 defined in intervals, and then with the H3 having jumps where the D8 branes are inserted. In this way, this H function, which is a cubic polynomial, you can, and therefore depends on 4 different constants, you can choose these constants. I didn't show you the form of the Ramon-Ramon fluxes, but when you integrate them, they will depend on these constants, and they will give you the quantized charges of the branes that are present here. So you can ultimately label the function with these quantized charges that you find in the different intervals. Okay? So what you have is these intervals in which the H function takes this form. The constants are going to be changing because H has to be continuous, and also its first and second derivatives. And this will tell you how the charges will be defined in all the regions R, L, L plus 1. At each integer L, we have NS5 branes. There is where we also introduce the extra D8 branes that we are using to glue the solutions. And then, based on these ingredients, we can already propose a Hanani-Witten brane setup underlying this geometry, from where we are going to extract the information about the field theory associated to these solutions. So based on what I told you, we have in the R direction the NS5 branes, which are these vertical lines. Then looking at the fluxes, we know as well that we have D2s and D6 that are stretched between the NS5 branes. The number of them depend on the interval, so it changes as we are moving in R. And then we also have a perpendicular D4 and D8 branes. But of course, this cannot be the whole story because we have a CP3 in our internal space, and this makes things much more complicated. So let's then decide to take the massless limit and see what we have there. Nicely, when we take the massless limit, we can do a change of variables going from R to this new variable mu. And in that case, we recover the ABGM geometry in type 2A. Basically, ADS3 and the R direction combine because you get this nice way of writing the ADS4. And if you look at the B2 field, you find the discrete holonomy that you have in ABJ. So when you remove the D8 branes, these solutions become ADS4 cross CP3. We know which is the brane setup that is underlying the ABJM theory. This is typically described in type 2B after you do a T-duality on this psi direction inside the CP3. So this is the brane intersection. You have the 3 branes that are stretched in this psi direction between an NS5 brane. Here I'm putting a prime on this NS5 brane because these are not the ones that I was showing before that were located along the R direction. Those are not there in the massless limit. They only appear when you switch on the D8 branes. So these are the ones that you find in ABJM when you go into the type 2B description. Okay, so you find one in an NS5 parent brane at psi equals 0, and then at psi equal pi, you have the bound state of NS5 prime and K D5 prime branes, and then on the other side of the psi interval, you find the other NS5 prime brane. Okay, and then you have these 3 branes stretched on the psi direction between the NS5 prime and the bound state, and N plus M because we are in the ABJ extension. So you find the fractional branes in the between the bound state and the NS5 prime brane. Okay, and there is this rotation between the bound state as it happens in ABJM due to this the charge of the D6 branes that after the duality became these D5 prime branes. Okay, you may be wondering why I'm using this N and K for the number of D3s, which are actually the number of D2s, and the number of D5s, which were actually the number of D6, while here I have Q2, Q6. Well, this is because you need to take into account that in these non-trivial topologies, we have the effect of the Fried-Witten anomaly and the higher curvature terms. And these dissolve lower dimensional brane charges in the work volume of a given D brane. So they contribute to the page charge that you compute. So the way the page charge is related to the actual number of D2 branes is through this expression, which involves also the actual number of D6 branes. Okay, and this is the precise way in which they are related, as these people pointed out. So, okay, we know then which is the brane intersection that appears in the massless limit because we have recovered ABJM. So now let's add the extra branes that we have in our case. In the massive case, we have the D8 branes, which in the type 2B description are now D7 branes. The way these are inserted in a way that preserves supersymmetries, in particular half of the supersymmetries, as I'm going to argue now, is lying in this the common work volume directions, but just in 2 of them, not in this one. So you find that already with this addition, the field theory is going to be 2-dimensional because we have a common 2-dimensional brane work volume. And the NS5 branes need to be lying in this direction. This brane configuration preserves if this part, which was what I was referring in my first slide, this would be the background branes, because I'm going to argue that these are the defect branes, and we are describing surface defects within the ABJM theory. Here, the intersection was 3-dimensional. Now it is 2-dimensional. Here we had you know, at the level of the brain intersection, we have n equals 3 and n equals 3 supersymmetry in 3 dimensions. When we are adding the defect brains, supersymmetry is broken by a half. Adding either one of them, the other can be added for free. And this means 0,3 supersymmetries in 2 dimensions. This is half the supersymmetries because 0,3 in 2 dimensions means 3 Poincaré supercharges, while in 3 dimensions means 6 Poincaré supercharges. Okay, so already from this brain intersection that I just showed you, one can draw nicely what is the brain picture that we have. I didn't tell explicitly that in fact, in this brain intersection, we have a brain box. We have our color brains are the D3 brains that you see. In ABJM, they were just stretching between NS5 prime brains along the side direction, but now they are stretching once we introduce our defect brains also in this R direction between NS5 brains. So these are constructions in which your color brains are like extensions of Hanani-Witten constructions. Your color brains are stretched between perpendicular sets of NS5 brains, the NS5s and the NS5 prime brains. So in this brain box model that I'm going to discuss now better, you see that we have here, I'm depicting the R and the psi directions. We have at psi equals 0 the NS5 prime brain. As we are moving in R, we have the NS5 brains. Here we have the bound state of the NS5 prime brain with the D5 prime brains. Now this bound state is composed of different numbers of D5 prime brains because as we are introducing the D7 brains in the R directions, we are creating D5 prime brains. So this is changing. Therefore, if you were just looking at this part, you would be seeing that you have the diagram, the brain diagram of ABJM. Here, I'm just adding the R direction. This becomes cylindrical, but it's not really cylindrical because in ABJM, you would have this brain rotated with respect to the NS5 prime brain. Here, it is rotated as well with a rotation angle that depends on where we are, because this number of D5 prime brains is changing as we are moving in R. So this is cylindrical only because I wanted a nice drawing, but it's not really cylindrical. But our color brains are plaquettes, say, because they are bounded between the two different perpendicular NS5 and NS5 prime brains, but they are in this case cylindrical because one of these directions psi is a circle. Okay, so I said that the brain intersection preserves 0,3 supersymmetries. Not much is known when you try to surf the literature about two-dimensional 0,3 gauge theories, but you may expect that as it happens in 3 dimensions, the field content of this gauge theory is going to be very similar to that of a 0,4 gauge theory, except for the deformations that are introduced by the rotations of the 5 prime brains that will render some multiplets massive. If it were not for these rotations, you would have a 0,4 supersymmetric 2D theory. And these are well known. There is a lot of information about these gauge theories, how they are realized in brain models, and in particular in brain boxes, which is what we have now. This was studied by Hanani and Okazaki, and we can borrow the results that they found. So indeed, when you have these configurations in which you have the 3 brains that are stretched between NS5s and NS5 prime brains, you have to look at the quantization of the open strings with both ends on the same stack of the 3 brains or on different stacks across NS5s and NS5 prime brains. This has been studied, and you find that the open strings that end on the same stack of the 3 brains have the field content of a 0,4 vector multiplet. If they are connecting the 3 brains across NS5 brains or across NS5 prime brains, you have the field content of what are called 0,4 twisted or not twisted hypermultiplets. These contain scalars, and the twisted or not twisted, well, right moving fermions, and the twisted or untwisted depends on which how they are charged. I forgot to say that these theories have an SO4R symmetry, SU2 cross SU2, depends with respect to which of the SU2s they are charged. This is the distinction. And then you can also find, this you find a bit shocking at the beginning, this field that is a 0-2 Fermi multiplet, which just contains a left-moving fermion. This is really necessary when you need to construct the superpotential of these 0-4 gauge theories. And it contains a left-moving fermion. It doesn't have any supersymmetric companion because the supersymmetry is realized on the right-moving fermion, on the right-moving sector, but it tells you how supersymmetry makes it interact with the right-moving fermions. Well, okay, these things are there, and this comes when you quantize the open strings that stretch between D3 branes across both an NS5 and an NS5 prime brane. Okay, so with all those ingredients, then we can construct which are the quivers that live in the brane intersection that I was showing you. These are very complicated quivers in which there are many types of different fields, but if you just look at this part, this is the R direction. If you just look at this part, you find something very similar to the quiver that describes ABGM. You just have the number of D3 branes. In our case, since we are also moving in the R direction and this number is changing as we move in R, this N changes as we move here, but we have the number of D3s, the number of D3s, including the fractional ones. And they are connected here with two 0-4 hypermultiplets because you can connect the D3 branes in the same interval going across the NS5 prime in 0 pi or across the 1 at 0. You have these two matter fields. Then you have, of course, the D8 branes that you have added. This will give you an extra flavor group connected with the Fermi multiplets. And what you had in the ABJM case, which was interpreted as the level of the Chern-Simons term, in this case, we are in 2 dimensions. This becomes a normal ordinary flavor group. So this by itself would be basically ABJM if these were 3-dimensional fields and we were removing this, the D8 branes. This would become the level of the Chern-Simons group and the theory would be 3-dimensional. These multiplets could be built as 3D multiplets. But here we have the R direction, so we have to couple these to the ones in R as we are moving in R, and this gives rise to extra multiplets. There are a whole plethora of different multiplets. So I was saying at the beginning that in some examples you find explicit realizations of these defect theories in which you see that you are inserting the defect branes, and this you can do it very explicitly at the level of the quiver. And this is what happens here. We are inserting the D8 branes, so we are getting this extra thin, and we are inserting the NS5, so we get all this extra thin. Of course, here one has to be careful how you define this globally, and what we did was to complete the space with 2 massless regions at the beginning and at the end. One can check gauge anomaly cancellation and all that, and this works perfectly well for these solutions. So here something nice happens, because what you see is that when you do this mapping between the page charges that you compute from your fluxes and the actual number of branes in its interval, what I was telling you before that you need to do in ABJM, you need to do here as well, because you add to that the contribution of the D8 branes, you find these relations. And then when you see how the charges are changing across intervals that you compute from your solution, imposing continuity of the function h and its 2 first and second derivatives, you find how n, m, and k have to also change as we move in R. And then you recognize that this is no other but cyberduality, as was proposed in ABJ for non-vanishing mass. This was proposed in a non-supersymmetric setting by Berman and Lifshitz. They took in ADS4 cross CP3, they introduced the 8 branes that they took as probe branes, ignoring their back reaction in the geometry. In a non-supersymmetric setting, I mean, the brain intersection does not preserve any kind of supersymmetries. And doing Hanani-Witten moves, they proposed that this Chern-Simons matter theory, three-dimensional, should be equivalent to this Chern-Simons matter theory. Here we are finding the same. We are finding the same mapping, this n plus m goes to n, etc., the same mapping, but we are in one dimension less. We are seeing the cyber duality as a large gauge transformation. We are realizing it geometrically. This is exactly the way you can do that in the massless case from the ABJM theory. These people showed that a large gauge transformation produces this change, in this case, ignoring the Q in the charges, because basically this is a brain creation effect that is taking place as you do these large gauge transformations. So the interpretation of this is that when instead of introducing the D8 branes as probe branes in a non-supersymmetric way, which is what was done by Berman and Lifshitz, you introduce them in a way that supersymmetries are preserved, in particular half of the supersymmetries, which requires adding as well NS5 branes, then the back reaction of these branes makes that the 3D field theory directions will now, one of the 3D field theory directions will become an energy scale and will generate a flow towards a 2D CFT. We will end up with a 2D theory instead of the 3D theory we started with. And this back reaction produces this ADS3 cross CP3 geometry where this extra direction has become part of the internal space. And here we are able to realize cyberduality geometrically. So now, well, this is a nice result that even if we don't know much about which are these CFTs associated to these solutions and how they could arise from gauge theories with 0-3 supersymmetries, we have a non-trivial prediction for the central charge that they need to have. Coming from holography, we can use the Brown-Eno formula, compute the holographic central charge from the internal volume, the volume of the internal space, and we find this neat result that should we be able to compute the central charge from the field theory using 0-3 multiplets, we should be able to reproduce in the holographic limit. So this is something that would be interesting to address. And now I may have 5 minutes left, or even less. So I will very quickly discuss these other solutions that we constructed years ago to massive 2A supergravity, which have a 0-4 supersymmetry, small, which means SU2R symmetry, and which have this form here. These are solutions that contain an ADS3, an S3, an S2. They contain 2 non-compact directions, and that we set out to try to interpret in terms of describing surface defects within some higher dimensional CFT. What could be this higher dimensional CFT? For those of you familiar with the ADS7 solutions to massive 2A supergravity that Tomasiello and collaborators constructed, this solution, here I'm just showing the metric, but this metric looks very similar to the metric that describes those solutions. Those solutions are ADS7 times S2 times interval. This is the interval in those solutions. This is the S2. And instead of having the ADS3, we have this ADS3, S3, and this interval. But other than that, they look very similar. This alpha that encodes the solutions is a function that depends on Z that appears already in the Tomasiello solutions. Through its third derivative is giving you the mass of the massive 2A supergravity where they live. And here, when you send this X direction to infinity, what you recover asymptotically is ADS7 crosses 2 cross interval. This is an example in which asymptotically you have the higher dimensional ADS space, and there are corrections coming from the fluxes associated to the branes that were not present in the higher dimensional ADS7 solution, which in this case is not the V2. The V2 was already present. This direction, I said, is non-compact, but in the paper by Tomasiello, it is explained how you make sense of this non-compact direction by ending the space with physical branes, D6 branes, orientifold fixed planes. There are different possibilities. So you have NS5 branes located at the set equal an integer. In the Tomasiello solutions, you also have D6 and D8 branes, and the field theory that lives in this intersection is 6-dimensional. It's a 6D 1,0 theory, which flows to a CFT and in the UV, and this is the one that is dual to the Tomasiello solutions. Here we have extra fluxes, which are associated to D2 and D4 branes, which are in this case the defect branes, which break the supersymmetry by a half, and which also render the full brane intersection. It describes a 2D theory because this is the common intersection of all the D2, D4, NS5, D6, D8 branes. So, okay, in this case, we have all the branes that were also present in my previous example present, because we can integrate the fluxes that I didn't show you, and we can propose a Hanani-Witten brane setup, which in this case is the one that I was proposing you before. We don't have CP3. Basically, you have this Hanani-Witten brane setup along the set direction. We have D2s and D6 stretched between NS5s, and we have perpendicular D4 and D8. The numbers are changing across intervals, and one can build the associated quiver in terms, in this case, of 0,4 fields, because this is the supersymmetries that are preserved. This is another example in which you see that inserting the D2s and the D4s, which are the defect branes, produces the quiver describing the defect CFT, because if you had the mother theory, the quiver would be described in terms of 6D 1,0 fields, and it would consist on these 6 color groups, with some flavor groups coming from the D8 branes. This is the number of D8 branes, and here you are inserting the D2s and the D4s in a supersymmetric way, and this is the quiver that you have. It's another way of seeing this explicitly. Here, I just want to, probably I will say it in the conclusion since I ran out of time, or I say it here and not in the conclusions. We tried to give an interpretation of these solutions as describing surface defects within 6D 1,0 theories, but we faced the same a typical situation in which we try to compute the contribution of the defects to the central charge, and we found still at this level, with a quite naive way of computing or taking care of the cutoff that you need to introduce, because we have a non-compact direction, we found that they were not contributing to the central charge. This was very shocking, and we decided to go and compute configurations such as baryon vertices, giant gravitons in both the mother theory and the defect theory, and compare them. And I'm just going to flash that when you do this for the baryon vertex, for instance, this would be the one for the 6D theory. This would be the one for the 2D theory. You have amazing nice cancellations that give you exactly the same size and energy for this baryon vertex configuration for both the mother and the defect theory. The same thing happened for the giant graviton configurations that we constructed. So we ended up proposing the interpretation of these solutions in terms of the constructed 6D 1,0 CFTs. We are still working on this because we want to make more precise the calculation of the central charge, but it could be that we are deconstructing these theories in terms of 2D degrees, 0,4 degrees of freedom. Here is just a summary of what I already said, so I think I will stop here. Sorry.
with time for 1 or 2 questions. Yes, Sakura.
Can you remind me, what is the R symmetry of the 0,3?
It's an SO3 R symmetry.
SO3, I see, okay. And you had these 0,4 multiplets and then the Fermi 0,2. And what was breaking it to 0,3 actually? And that country wasn't.
Yeah, I was very fast describing this, but the quivers that I saw are built in terms of 0,4 multiplets. And then when you take into account, there you are not taking into account the rotation of the branes inside these bound states. When you do that, there are some matter multiplets that are no longer there.
Some of these become massive, but how?
Yes, some of them, the scalars that are transverse to some D5 branes become massive, and you don't need to count them, for instance, for the gauge anomaly cancellation. But the quivers are 0,4 because we couldn't find any explicit way of realizing them in terms of 0,3.
Can I ask one more question? What is the status of this whole, what kind of M, N supersymmetries can one have in super control field theories? Like, now you found 0,3, but is there something like 2,1, or what are the combinations? Is there some development in that pinning down what is possible?
I wouldn't be able to tell you. I don't know.
It's always very confusing.
I think there are still many possibilities that have not been explored, but step by step, we are narrowing down.
Okay, so we're out of time, so let's thank Yolanda again. Now we have a lunch break. Lunch is just outside where we had the coffee break. No problem. No problem.